Hello. Are we here now? Okay, cool.
Hello.
Oh man. Okay. Hello. Hello, everyone. Are we hopefully audible?
Assuming y'all can hear us.
Somebody say something in the chat if you can hear us, please.
Yeah, you're good. Hi, everybody.
Okay, cool, cool. Thank you. Hello, welcome to the first time we've tried to do something new in the middle of the night while we're not at all stressed about doing work at the same time. I am Rebecca Larson. I am a PhD student at the University of Texas at Austin. I am one of the hosts of Astronomy on Tap Austin, or Astronomy on Tap ATX. And with us tonight is our lead for our observing run. Do you want to introduce yourself?
Yeah, hi, I'm Taylor Hutchison. I am also a graduate student, a PhD graduate student, but I'm at Texas A&M University. And this is some time I was awarded through NASA grant for the Keck Observatory. And so it's really exciting. We're remote observing.
Hey. So we also have our Astronomy on Tap Austin co-host, Dr. Michaela Bagley. I don't know where your video is because I think I spotlighted something.
That's cool. Hi, everybody.
One moment.
I'm just here to hang out a little.
Hey, there we go.
There you are.
Okay, so our plan for tonight was to kind of show you what it's like to be an astronomer. Like, what is it that we actually do when we go observing? Right now, we've currently invaded my boss's office. And so we are not, unfortunately, at the telescope. We are remotely controlling it from the university campus. And so we can walk you through kind of like the steps on how we do things and talk a little bit about what we're looking for and why we're using this. And if you ever have any questions or you want to see something specific, please just in the YouTube chat, go ahead and talk to us there. We have plenty of coffee and things to do, and we have a somewhere we have an animal. So we can actually, one of the perks of, and there's a cow. One of the perks of being remote is that we can have observing assistants that don't have to fly all the way to Hawaii. So John, it's sad that we don't get to travel to the observatory to do our observations. But it's very fortunate that we don't then lose our access to the telescope at times like this. And so all of the people at the Keck Observatory have worked very hard to make remote observing a possibility for us. And that's been incredible that we still get to use these facilities even in times like this. So I'm going to just kind of let Taylor talk to you a little bit about what we're even looking for, and why we're using this particular telescope. So in the chat, we have Yazwant from Astronomy on Tap, Bryan College Station, where Taylor is as well. And so if you have any questions for them, they're also here. And then John O'Meara is one of the lead people at the Keck Observatory. And so if there's any specific Keck questions, we'll probably just ask him since he's the expert. We also have with us on a separate Zoom call people who are physically located at the telescope and helping us drive it. And so if you have questions for them, we can also get them to help answer some of those things that you might want to know. And this is Jasmine. So if you want to talk to Jasmine, she's going to go away now.
So yeah, by the way, if you happen to notice a cow that makes sounds a lot, that's the sound we've chosen for when the telescope finishes taking an image. And so you're going to hear that every 2 minutes for the rest of the night.
That's the image.
Yeah, so what you're seeing here, it might change. Right here is the image. It's just a ton of different kinds of spectroscopy. So it might blink when it changes to the next image that just got taken. But yeah, so you can hear a cow every 2 minutes, and it's going to be kind of loud, but
a little bit.
Yeah. So in general, what we're doing is we're taking spectroscopy of some of the most distant galaxies that we have ever found so far, just in general. Like, so the universe, for example, is about 14 billion years old. And we're kind of at present day, but we're trying to find some of the earliest galaxies ever and the most distant galaxies. And so the galaxies we're looking for, existed when the universe was only 1 billion years old. So less than 1 billion years after the Big Bang. And so we're essentially looking for galaxies whose light has traveled over 13 billion years to reach us. And so that means really hard to find. They're very faint, they're really far away, and the light that we're seeing, because of the amount of space it's traveled and the fact that things are moving away from us because the expansion of the universe, the light we see from these galaxies is just displaced to significantly larger wavelengths. And so the first light you see from these galaxies is in the near infrared. And so that's why we use these amazing spectrographs, like the Mossfire spectrograph at Keck, to try and find these galaxies. And the really cool thing about Mossfire, and the reason why I always gush about how much I love it, is because no one knows. But no, so Mossfire is what we call a multi-object spectrograph. And so it can look at many different things at the same time.
Multiple objects?
Multiple objects, you could say. So like with a normal spectrograph, I'm going to use my notebooks as an example.
Oh my goodness.
With a normal spectrograph, you might have one slit, right? And so you essentially, like with your eye being the telescope, you have the slits zooming in and you're just looking at one thing at a time.
Why do you have a slit?
You have to block out all the other light and just focus on this one thing. And so with a multi-object spectrograph, you're doing the same thing, but you're doing it for a ton of different sources. And that's really cool. And so the reason why you see all these different bright lines and they're all slightly shifted horizontally is because we have, I think, like 30 slits here that we're looking at. So 30 different objects have a slit that's assigned to them. And so we're going to get spectroscopy of 30 different things.
All at once.
All at once.
Efficiency at its
It is
finest.
super cool. So yeah, Mossfire is amazing. And that's how we can look at and try and find all these galaxies and get spectroscopy of a lot of things at once. And that's really the most efficient way to try and do the science that we do. We'll be staring at the same field of galaxies for the entire night because they're so faint.
Yes.
So yeah, there's the summary. That's what we're doing tonight.
Yeah.
Thanks for joining us.
Yeah, so we can kind of talk a little bit about some of the things that we have already done. So we were a little bit late starting because we were waiting for the specific part of the sky that we're staring at to be high enough for. Jasmine, can you be quiet? For that specific spot that we're staring at to be high enough for the telescope to actually be able to see it. And so we took a spectrum of a standard star. So there's data that we're taking of distant galaxies that we don't know a lot about, and what we want to know is more about them. And so in order to make sure that we have a good idea of the measurements we're taking, we use some kind of standard. And typically what we use is a star. And so the first thing we did was we took a spectrum of a star, and this is distracting. We took a spectrum of a star that we know a lot about. And so we can then take that spectrum and use what we know about that star to calibrate the data that we're taking of our galaxies later. And so that's what we were working on, making sure we had all of that. And we were focusing the telescope on our spot on the sky. And so we were a little bit late getting started because we wanted to make sure that we were good to go and there were no issues before we decided to talk to you people at the same time. I didn't even look at the data. Is the data good?
Yeah, I think so. I'm gonna open it on here too, so I can look at that.
Yeah. So if you have any questions about what we are doing, and I can't, you can't see that we have 2 laptops, 2 screens, and a TV over here that's also connected to a laptop. And so, and the live stream is somewhere on an iPad.
Propped on 16 textbooks.
Yeah, of the same copies of the same textbook.
At some point, you'll give us a tour of the room, right?
Yes.
Yes.
We absolutely will
Nice.
show you the setup we have. So the reason we're not sitting in our apartments is because of internet, and for also the numerous screens. Typically when we observe at the observatory, we have 4 screens and a TV or 2 and
3 laptops.
and our laptops. And so that sounds a little bit excessive, but right now there's 4 windows that we have open to control the telescope with. And so if you only have one screen, you cannot see all of the things that you need to be watching. And so you'll see us occasionally staring around the room at all of the different things that we have open to make sure that nothing is going wrong.
Do you want to do a quick like revert camera and show the whole thing?
Yeah, well, I'm just gonna pick it up because I don't know how to do that.
Okay.
And we'll try to, excuse me, dog. We'll show you where we are sitting. So here is can we see it?
Yeah.
Okay. So here is where we're sitting. So we have the TV hooked up and we have all of the monitors and then our giant stack of textbooks. And so we have all of the different control windows open on varying different places. And of course we have help,
Little dog.
who's not helpful, just very bored. Okay, so I don't want to make anyone dizzy. And so I'm trying to do this slowly.
Perfect.
Okay, cool.
Angle it slightly. Awesome.
Okay, cool. Thanks, Alan. Yeah, we tried very hard to replicate the setup that we have in Hawaii. And I still want more monitors. So
We can always do more.
yeah. Okay. So I have.
So we could show the Myra video if you want.
Yes.
Okay, so to kind of explain.
Where is my mouse?
I don't know where it is. It's over here.
Anyone?
It's
Okay,
over
it's over there.
So we wanted to show y'all. So when you first start at the telescope at night, one of the things that you have to do once you're able to look at the sky, so when it's dark enough that you can open the telescope and start looking at stars and other things, you have to focus the telescope. Very similar to how you'd imagine, like with a camera, you're turning that little dial to change the separation of the different lenses to try and focus your camera. And so the cool thing about this is whenever you focus the telescope, like the Keck telescopes, it has a 10-meter diameter telescope. So it's about 30 feet wide. It's a massive telescope. And it's made up of 36 segments. And so 36 hexagonal mirrors, much like the ones you see right here. These are the two Keck
Almost
mirrors.
like that's a Keck
Almost
pin.
like this is a Keck pin, which it is. So the cool thing is what it does, we're going to show you the video of it. So what the operating assistant does is they open and then they close essentially all the segments. And so you're going to see essentially this cute little footprint of the Keck telescope. You'll see the 36 little dots. And then it's going to close it again to focus into one star. And so it looks at a star to do this. And so Rebecca's going to show you a cute video.
It's a really cool little telescope selfie.
Yeah.
Where do we think we put that? I think
She has a lot of windows open.
there's so many things open right now. Okay.
Is this the video?
I think this is the video. Yeah. Okay. So you're looking right here. So here she's moving the telescope for us to find the star that we want to focus on. And so what you'll see here is what Taylor was talking about is the reflection of all of the different mirrors. And so there's two different stars right here. And so what you're actually seeing is both of these stars reflected onto the mirrors of the telescope and then back up onto the secondary mirror. And that's what you're getting an image of, is the light of that star reflecting on all of the, and you'll see them kind of moving around as we try to focus it. And then, like Taylor said, bringing it back to a point so that we can make sure that we are measuring how focused we are. Mm-hmm. But also, it's just a really cute picture of the telescope.
It's kind of like Keck is saying hello.
Hello.
It's the hello, good morning.
Yes. Or good evening, because it's night time.
True. I mean, morning for astronomers. We're observing. We sleep all day.
Yes. So this, while we're here, is a screen, one of the many screens that we have open that controls the telescope. So you can see on the bottom right here, we have a bunch of like where we're pointing and coordinates and dates and times and information about like the position of the telescope. The top right has information about the measurements of the weather at the summit in and outside of the dome of the telescope. And then on the left is one of the control panels for focusing these things. So now you'll see it go back.
Shrink back down.
Look at it.
And we just got little stars.
And then it's gonna refocus again to test. Wow, this is a long video. But yeah, so I this is one of my favorite images that we take, because you can see a little picture of the telescope that you're using. Do you want to talk about like what we're doing versus what they're doing at the mountain?
Sure. So we'll give you an actual tour. We'll give you an actual tour of all the different little control panels we use here, because there's 4 of them. But for now, just the kind of the way to describe it, the reason why we can remote observe is because we are controlling the instrument. But the people at the Keck Observatory are the ones who are controlling the telescope. And so for, in a night taking data, you get to talk to the person moving the telescope for you, because we are not allowed to do that because this is a very expensive telescope.
I don't want to do
like
that.
Roughly like, John will correct us if this is wrong, but I think it's like $100,000 a night if you were to like purchase time out of pocket to get time on this telescope, like one night for one telescope. That's how much it is. So it's just insane. But so they run the telescope. We're not allowed to touch it, but we are allowed to control the instrument. And so it's essentially, imagine you have this. Oh, actually, I have a really great diagram for this. We'll show you a diagram in a little bit.
What?
If you open the paper, nice gray paper, one of the images shows the Cassegrain.
Oh yeah. Oh, that's a good idea.
So she's gonna pull that up. But so essentially you have, a few different mirrors, one of them being the 10-meter wide mirror system. And then at the very bottom, like in the center, right underneath where the big mirror is where we have our instrument. So imagine it being kind of like a camera down there, except it's a spectrograph. That's the way that we're taking data. And so we just get to control, when is the instrument on, when is it taking data, how we want it to take our data. We're doing 2-minute exposures. And so all that really means is imagine you have a camera and you're opening it up and you're just like, it's just exposing an image for 2 minutes. This is my opening up.
All of it. So
all of it open. It's kind of like those pictures, if you've ever seen them, of like a really cool picture at night and someone takes a light and they spell out a word because you've exposed a camera long enough to where it's just caught all of that light. It's the same thing, except we're staying very still. Yeah, it's perfect. Cool. So Rebecca's going to show you what this looks like. This is from a recent paper I did, summarizing some work I did as a Keck visiting scholar at the observatory. So what you're seeing here, if you want to zoom in more, the left-hand side is showing you the way the 2 systems work. So this the system is it's similar to what we call a Cassegrain instrument or telescope design. And so you essentially have your big primary mirror where the incoming light hits. It reflects off the primary mirror up to the secondary, which is, you see it as like a gray cylinder. That's just because the little secondary mirror is pointing towards the primary mirror. And then it reflects off the secondary and down into the center of the primary where the Cassegrain focus is located. And then if you look on the right side, that's beneath the underside of the big primary mirror, and that's where our spectrograph is located. And so that's all the light gets tunneled and funneled into that little spectrograph, and that's how we get our data. And then we just control when we're taking images and stuff. And so that's how we play. That's the role we play when we use it.
This is the thing we're controlling.
This is the thing we're controlling.
This is the thing they're controlling.
They control everything else.
Yeah.
And these telescopes also live inside of domes, which protect them from the elements. And so the dome will rotate as the telescope's moving around. And so it's always looking at the sky. But they do all of that. We don't do that.
They are the experts.
We trust them. They've been trained and are highly skilled. But
yeah. So John has mentioned some of the things that we've done with Mossfire.
So sweet.
John, you're awesome, and I appreciate the hell out of you being here. Yeah, so Taylor talked earlier about like what science we're trying to do. So we're looking at things that are, 13 billion years old. The light has traveled a long time and it's very faint. These things are very distant and very hard to detect. And so, hi Cameron. And so what we're trying to do is kind of push the boundaries of our current technological capabilities. And Keck is the best telescope out there to do our science. And it is still very hard to do what we're doing. So we are, like Taylor said, staring at the same thing for like the whole half night.
Yeah,
the whole half night doesn't make sense. But they were staring at the whole, like one spot over and over and over again. We're taking a bunch of pictures over and over and over again, hoping that we get as much of the light as we can so that we can see these really, really faint things. And so it turns out that's hard already to find faint things. And it also turns out that when you stare at one thing for a long time, the Earth is spinning, you know, as it does. And so we have to continually focus on one spot of the sky, but as the Earth is turning, we have to move the telescope along with it. And so we use these stars to kind of guide the telescope. So we look for bright things that we kind of like guide the telescope with. And then we also are taking multiple different images, and then we have to put those all together. And so the problem we run into is that what we're trying to do is look for something very small, very faint, and very hard to detect, but adding a bunch of things together and trying to track it across the sky through one night, and then adding multiple nights of that kind of data together. All of those nights have different conditions. Maybe there were clouds one night, maybe there was humidity, maybe there was some other situation like a volcano and ash and stuff in the sky. And so because we're observing from the surface of the Earth, we have to deal with looking through the atmosphere, and that is quite variable and changes a lot. We have to deal with, again, moving through space as we do. And so we are dealing with a lot of different factors. And typically, if you are looking at something very, very bright, you can just look at your data and be like, oh, there's the thing I was looking for, I can see it. But unfortunately, what we're looking for, you have to stack all of that data you took over multiple nights together to even see it. But in order to line all of that data up, to stack it together, you have to be able to see it, to stack it, to line it up. And so we're kind of in this catch-22 of like, I can't see what I'm doing, but I need to stack it to see what I'm doing, but I need to be able to, if any of that made sense. Mm-hmm. And so we've had to go through a lot of different trial and error and small and somewhat significant improvements to how typical data is used from this telescope to account for things and in slight imprecisions that we were finding in our data, which most people don't have to deal with since they look at things that you can see much easier than what we're trying to do. And so we can talk like more about that if there's specific questions, but hopefully some of the things that we found have been accounted for and measured, and we did our best to write that all out and measure that. And part of that paper that we just showed was Taylor went to Hawaii for some number of months, 2 months, to work on this and to build in all of these improvements that we were using for our data into the way the telescope operates, so that anybody using it in the future can benefit from those improvements that we've made. And so that paper that it just came out. Yeah, it just came out. Talks about the things that we found and how to account for that in everyone else's data as well. And so all of the suffering that we went through, we tried to share the results of.
And also one of my co-authors on that, the person I came to Keck to work with, Dr. Josh Wallabinder, who's a support astronomer and is wonderful, is also our support astronomer for tonight. And so we'll introduce you to him at some point. He's still around.
Yeah, he's in the computer.
He's over here.
The other computer. Yeah. The secondary mirrors we're talking about. Does anybody have any questions? I mean, we can talk about whatever. What we're doing right now is we have, like we said, we're staring at the same thing over and over. And so we have basically a macro running to continue to take the same exposures. And every time you hear a cow, it finishes one exposure and then updates that image. I don't know how to point to that thing. It updates this image with the new one it just took. And so you'll see us kind of glance over and make sure nothing looks insane. And then we will let it keep doing this repeatedly throughout the night. And so oftentimes, because you don't always get to look at 30 things at a time, you move around and look at different objects throughout the night. We just stare at the same thing over and over and over again. And so we're a pretty easy group to observe with. Since we just go ahead and repeat. Of all the noises, why a cow? Because y'all want the other noises are worse.
There are a lot of noises. We could have Captain Picard say engage.
Engage.
We could,
Yeah.
we'll switch that one for now.
No.
Just for a second,
Okay.
so they can hear it. We'll show you all we'll feature some other noises for you tonight.
There's a whole like control panel of noise. You want me to show the control panel? Since I have the ability to just show people things. Engage. Are you here?
We'll leave that one. I'm on it actively right now. If you want to use it, I can get off.
No, that's fine. I can show what you're doing, right?
Oh, yeah.
Duh.
All right. So here is where you'll see this. Actually, you're about to see it change. So we're going to go look at a star. This white horizontal line you see is actually the signal of the star. And wait, it's going to update. There you go. So this is the new place. And you see that it actually shifted from where our pixel was originally. If you look up where my mouse is up here, this thing, it shifted. And that's because we're using what's called the dithering technique, which we can explain later. But over here is where we control the sound.
But over here is the important part. This is the noise that it can make.
So you just heard Captain Picard, but we can switch to something else. There's a Homer Simpson one. Where is that? There you go.
Oh my God.
That's really annoying though. Essentially, like when the first time we ever observed on this, the second time I went, the first time Rebecca went, when we went to Hawaii to observe, this is back in like 2018, I think.
Yeah.
We hated the default sounds. And so we went through and tested all the sounds. Some of them drove our support astronomers and always crazy. And we ended up just settling on the cow because it makes us laugh every time we hear it.
Somebody mentioned that it was because of Texas, and that's not exactly wrong.
Yeah, you're not wrong.
What does splat sound like?
Splat?
Yeah.
You can right click it and it'll play it. Oh, that's boring.
That was uneventful. Okay, I'll leave the cuckoo up and we'll hear that one. So you can also right click on it and make the sounds, which is why y'all been hearing it.
We can take votes later, but I swear if you make me listen to the exposure complete sound, I'm going to stop the live stream. Okay, we have questions.
Yes.
So John wants to know, why are the exposures so short if what we're looking at is so faint?
That's a great question. Although I would argue that 120 seconds is not short. But
Well, I mean,
relatively speaking, yes.
like if we need hours of time, like we basically need to open the camera and stare at this thing for hours at a time.
Mm-hmm.
More hours, the better, right? So like, why are we only taking a 2-minute exposure each time? Oh, sure. Okay. So right now, what we are dealing with is like you open the shutter for so long and there's cosmic rays. And so what can end up happening is these are like, I don't know how to explain a cosmic ray. Basically, it like lights up your camera and they're random and they will hit your detector and they'll be like really, really bright spots. And I can show you, we can zoom in on some so you can see. Oh my God.
That was a good one.
Oh.
I'm gonna go back to Cal and then I can zoom in on.
Yeah. So let me put the share screen back. So we can show you what a cosmic ray looks like. And so if you open it too long, it will completely cover your entire detector. And so you'll end up not being able to see your data because all of these things will be kind of in the way. And so it's basically what it looks like on your camera when you open it up is a hot pixel. And so if you've ever had like a computer screen that's gone bad and one of the pixels is just like, where's the space squid?
Oh, that's more of an artifact.
Yeah, but it's pretty. Okay, so you can see all these little bright spots in our image.
Ignore the lines, the vertical lines are, we expect those. We'll explain what those are in a second.
Yeah, all those little tiny dots in there. And so if you take exposures for too long, you get too many of those. And what we have to do later is take them out. And so you want to get a good exposure that balances your exposure time versus like how many of these things are kind of in your way. And then also like the sky background, basically like the background of space. The dog is done. The background of space, we also need to kind of remove that. And so you don't want to get too much of it to where it's too bright for you to remove. And so we split up our hours of observations into little 2-minute chunks.
Mm-hmm. Yeah. Also, because here we go. There are also some artifacts that are just going to happen with instruments because that's just how life works.
They're old.
And so we call this a space squid.
It's what it looks like to me.
Because it, you know, the little squid body here and the little legs come out. And so what's cool though is if we were to, let me zoom fit this again. So a cool thing about this particular image viewer is we can press tab and it shows you the difference from the previous image. And so I mentioned before that we have a dithering technique. This is why you see a white line here and a black line beneath it, because we're doing the subtracting these two images.
What's a dither mean?
Yes. So the dithering is a thing we do when with spectrographs. I'm sure some still do this, but when you're taking spectroscopy, you also need to account for the background sky and how bright it is and all the different things that come with that, especially in the near infrared where we have a lot of these annoying vertical lines, which we call skylines. And so what you do is, like some spectrographs, especially in the past, they would look at the object and then they'd move away off of the object to a, you know, quote unquote blank region into the sky and then take in the same length of image and then go back to the object. And they just essentially jump back and forth so they could properly account for the background noise. But when you have these kinds of instruments that are really efficient, the way you can handle this is called dithering. And so rather than moving off of your targets after each frame, you can just slightly move where you're looking at with the instrument and up and down, so dithering. And so you're changing the location where you see this horizontal line of the star, for instance. You're changing where your object is and it's slit every other frame. And so whenever you do your data reduction at the very end and you make this really nice, clean final spectrum, you have the background sky already accounted for because you've been doing this dithering technique. And so it's really useful. And MOSFER is very good at it. And so you'll see this effect anytime you do this tab thing to see the two different dithers. And so that's how far apart this object is for each dither.
That's how far you're moving the telescope.
Yeah, that's how far we're moving the telescope. We have a very tiny dither, but yeah. So to quickly describe what these vertical lines are, because we hate them. This looks really pretty, I'm sure. I thought it was gorgeous the first time I saw it. But these are actually, did you explain skylines? Okay, these are atmospheric skylines or OH emission lines. And so the atmosphere gets really excited and is emitting a lot of light. And so through various things. And so that light is unfortunately captured by our telescopes in the near infrared. And so the nice thing about it is they're consistently at the exact same wavelengths every single time you see these features, which is great because it'd be awful if they moved around. So the good part about that is you know exactly where they're going to be, and so you can correct for them. And so we actually leverage this in the near infrared, like MOSFER, for instance, leverages this and uses it to help them come up with what we call a wavelength solution, where you can look at a spectrum and know exactly at each pixel what that wavelength is. And so the skylines are actually really useful there, but the annoying part is that they might block your data. Like if you have an emission line from a galaxy that falls on a skyline, you're probably not going to see it. So they are still the bane of our existence, even though they're cool.
They look cool, except
cool.
I want them gone.
Yeah, they're not cool though.
Yeah.
It does get, H-band is probably the worst. This is the most of these white lines you probably see. But when you get to the K-band, for instance, you have fewer of these lines, but things start glowing, like the Earth is glowing.
What is K-band?
K-band is a larger wavelength region. So what we call a redder wavelength region. So, yeah.
So we have a question about the,
Sure.
oh yeah, sure. About the visual magnitude of the stars or the objects that we're looking at. How bright are your targets?
Well,
Fun fact.
the galaxies we look at are fainter than the night sky. Arguably, almost every galaxy ever is fainter than the night sky. When you look up at the sky, you are really only seeing stars in our Milky Way, and you see the large Magellanic Cloud and small Magellanic Cloud. Those are the two like non-Milky Way things that you would see by eye. You'd have to be in a really faint place there to kind of see all that detail. But the cool part is, as you look up in the sky and you're seeing all these great stars and these beautiful constellations, you're also accidentally looking at millions of galaxies. Like if you were to draw a tiny little dot on your thumb, like with your pen or something, just draw like a tiny little dot, and then you hold it out at arm's length and you like look up at the sky, that little dot would cover 1,000 galaxies or more. Like,
oh,
it's an insane amount. Oh yeah, which we can show that in a second.
Mm-hmm.
So we can't see them by eye, and this is why we need fancy instruments that can expose for longer than our eyes can. You know, this is all useful. So the stuff that we look at is incredibly faint. And so MOSFER is able to handle in weird Starmer units. things that are, 18th magnitude, which is, it's actually pretty faint. For people who work with stars, that would be, they would hate that, I'm sure, unless they're working with really small stars, which would be fainter.
No.
But that's really great for us. The stuff we look at is what we call, it's like 25th magnitude, which weird astronomy units, the larger the number, the fainter it is. These things are so faint that we needed the Hubble Space Telescope to find them. And even then we're pushing the limits of that. And so that's why we need like these 6 hours or more using a fancy instrument like Mossfire on Keck to even possibly detect light from these galaxies. And so they're incredibly faint.
Yeah.
So
just a bit. Yeah. I don't know where I put the chat. Oh, it's here. Yes, the Hubble is a deep field. Yes. Oh my gosh, that's what we just pointed at. So we both went. So right now we have taken over my boss's office, and we showed you a little bit of our setup, but we didn't show you what he has behind you. So we're gonna turn those around.
try turning the camera. It's gonna be an option.
Yeah, but they've got the case on the iPad.
Oh, you done messed up.
Look, I don't know. I didn't know. Oh, sorry. This is awkward as hell. Okay, so this is, I don't want to move too much. I feel like I'm going to make people dizzy. So this is a print, which is super, super cool, of the Hubble Ultra Deep Field. We actually have a talk on our channel, which I can find a link to and put in the chat, of the story of how this kind of came about. And so this is just a small spot on the sky that the Hubble Space Telescope stared at for, I don't know, Michaela, 1,000 hours or something like that. I don't know.
Yeah, something like that.
Something insane like that. And found so many galaxies. So all of these different points of light that you're looking at, with the exception of like this one with the rainbow in the bottom right corner and a couple others that have that same kind of pattern, those are stars with the little diffraction spikes that look like, like cartoon stars. Every other point of light is a galaxy. And so this kind of changed a lot of astronomy, because holy bejesus, that's a lot of galaxies and a very small spot of the sky. And then if you want to see the other, the other one who is bored as hell, do we want to show the imaginary telescope wall? Jasmine.
I think two of them are actually imaginary.
Okay, so he also he painted. Isn't it beautiful? Okay, so we also have a picture of the James Webb Space Telescope. Can you knock? I don't have a drink to take. Can you knock on? Thank you. Which is due to launch next year. And then this is a mock-up. So that's not a real picture of it in space, because it's not in space yet. But it does. But there, yes, we can show you a real picture of the telescope. It exists on the Earth right now. It needs to get launched into space. And then I'm so sorry, this is shaky. I should not be doing this. Then this is the Giant Magellan Telescope that is currently under construction in Chile, and it has some really cool lasers and big mirrors. And then another picture of the deep field, and then that is a picture of the Hobby Eberly Telescope out in West Texas that the University of Texas runs through McDonald Observatory. And so two of these exist in some form, but are not functioning yet for science. And then this one we use.
Is HET 36 seconds?
HET is, I don't know.
Sorry, I threw you under the bus.
I don't. I use Keck because right now I'm a Keck fan, especially since we're using it currently at the moment.
So we need sensitive.
But I don't know.
I think HET is 10 meters though, right? Yes.
Yes. Yes.
HET is the same size as Keck Observatory.
Yes, but it doesn't work the same way, so it can't do.
It's like it's 10 meters, but it's like an effective 8.8 or something like that.
Yeah.
Mm-hmm. There's
the size of Roosevelt's eye. That's a good description.
What?
I just said a dot in the thumb. I like that much better.
Josh, thank you for chiming in on the chat. Super appreciate that. We can show you on the camera
He
if
just walked away.
you
actually.
want to.
Timing.
Okay, well,
He'll be back.
he'll find that in a second. Ooh, the black hole image is beautiful. That was freaking revolutionary. Basically, we talk about telescopes as far as like the size of a telescope. So 10 meters is a big telescope. GMT is going to be 30 meters, so it's going to be a big telescope. And except it doesn't exist yet. We have pieces of it. Hang on.
We
have
also have
pieces of
the
it.
model
Yeah, we do.
with a little person. Is the person there?
Is the person there?
It's usually like a little tiny scale person.
I'm pretty sure Steve's kids broke that.
Oh, okay.
Well, this is a little model of the GMT. So each one of these mirrors is ginormous, and the whole thing is going to be like 30 meters, and it's going to spin around kind of like this, and then like rotate in this kind of direction. And then there used to be a little person for scale, but I don't. Oh, JK, it's right here. There's the little person for scale, and then here's the giant telescope. And so, why is the person in the back?
You
Whatever.
can move it. It moves.
No, like the little person.
It moves.
Doesn't.
Oh, nope, it doesn't.
Doesn't. Yeah. So this is the GMT, the Giant Magellan Telescope that's under construction. And then we have a piece of the mirror. So the mirror is made out of glass. We're just gonna go through all of my boss's things. That's what we're gonna do. He'll watch this later and be like, "Stop touching my stuff." So this is a piece of the glass used to make the mirror segment for those big mirrors. And so they do, this is like a broken piece or just like leftover scrap, but it's actually the glass they use to make the mirror for the telescope. And since the University of Texas is a owner in this and has paid parts of the money to build it, then our department gets fun toys
But
like that.
plug. So is A&M, and A&M's also building an amazing spectrograph.
Yeah, they are. Yeah.
So, just, you know, not that it's a competition of which school is better. But
Thanks, John. Yeah, each of those GMT mirrors itself, like each of them is 8 meters. And so it is like almost the size of Keck in each individual mirror. And so yeah, Josh is, yeah. So the instrument that we're using on the Keck telescope right now is Mossfire, like Taylor said. And Josh, the person here in the chat that we've been talking about, is the person who's like the instrument scientist.
yeah, he's like the lead instrument scientist for
the
Mossfire.
expert. Yeah.
The expert, which is why I worked with him.
Yeah. I thought there was another question that I forgot about, or we were going to talk about something else.
Michaela, is there anything you'd like to
Michaela.
input? You're here still.
Michaela's used Keck, but differently.
Yeah, you've used different instruments on Keck.
Yeah, I only went to Keck once, and I went right at the end of the before times.
Right at the end.
So did we.
Yeah.
Yeah.
And that was my first time at Keck, and it was amazing and awesome. And we had terrible weather, but otherwise it was amazing and awesome. It was like a magical experience. Oh no, I don't like being spelled.
I had to find the Zoom window. I was like, where is Michaela on my computer? Yeah. So hi Michaela. How are you?
Hi
Boss
everybody.
go there?
No, he's asleep. He's definitely fast asleep.
She's a dog as well.
Yeah.
Sometimes he photobombs AoTATX shows, but
Good stuff. Okay, so I guess we'll how do I buttons? Hey, cool. Okay. Yeah, John, I want to talk to you about the current weather on the summit right now.
Can you fix it?
Can you not? Can you get out with a fan and like blow all of the clouds and the humidity away? Just like fix that a little bit for us, if you don't mind.
Please, thank you.
There's a question about the software that runs it and how old this interface is.
Well, I can at least tell you that Mossfire came online in 2012. I'm pretty sure the software that's used is older because it looks the same. Or at least the base software looks similar between all the instruments, but I feel like John is probably better to answer that. I don't think it's the different GUIs and stuff I think are custom written, but I think it's all built from a base software that's usable. But John, please correct me if any of that's wrong.
I know, John. I know, I like having you here. I really do. But you and the seeing are just
Not friends.
not friends. So yeah, there's a couple more control panels. I don't know how many we wanna
We can show all of them.
show.
I need to restart the repeats real fast. You're gonna hear a witch go off.
Ooh, we get new sounds.
So we can set how many times we want it to take an image, and just for safety, I guess, we just make it do 20 images, but in pairs of 2, and pairs, that's a redundant phrase. 10 pairs, and so 20 images, and so then we make it stop. And so then we have to press restart to do the next 10 pairs. So you're about to hear a witch go off. That means that these 10 pairs are done and we're about to start the next cycle. So it's gonna be a cow and a witch at the same time, I think. 3, 2, 1, 1, 1. I counted too early.
It tells you the time.
I know. Oh, we're in the second frame. 1 second. 120 more seconds and then we'll hear the witch. We're doing great.
It's the first part of the night.
You're only like 45 minutes on Sky.
We're not going to get better than this. That's for sure. Yeah. Okay. What were you saying before that?
We can show the other GUIs, but I was going to run this again first, so we don't have to worry about that.
Sun. Yeah. That makes more sense.
Thank you, John, for explaining it.
Cow witches. Yeah. Yeah. We have we are all about variety. We have a train too, don't we?
The train only happens when we
Yeah.
change the mask. But
And the
it's
photon torpedo, I think is the other thing we have.
which is usually happens pretty quickly.
Which I don't think you'll hear. No, because we did all that stuff
We're
already.
only staring at this for the rest of the night. They won't hear the train or the photon torpedo.
There are a couple newer interfacey things, aren't there, John? That are or have been updated.
I think HiRes just got like a big update.
HiRes.
HiRes is one of the older but amazing spectrographs.
Yeah.
They have really gorgeous flats, which is just a calibration image. But and I realize I might be the only one who thinks that. John might. John loves HiRes. But I think it just got an update recently, which is really exciting.
Nice. Yeah, John, thank you for coming by. I super appreciate you coming in, and it's not the same not being able to come visit you to do all of these things.
Bye, John.
Everyone should go follow John on the internets.
He's cool.
I love HiRes. Of course. Let me real fast do this. Here is where you can find John on the Twitter.
Okay, who's the witch? I don't know if y'all could hear that,
That was great. John wants to know what the seeing is. Did you do the thing?
Wait 1 second. Don't go, John.
When we did Mira earlier, it was 0.9 arc second seeing.
But I will give you an answer in 1 moment.
Wait, Sam, are you talking? Wait, what instrument has a Star Trek red alert? I heard a cow. Yeah, the cow was followed by the witch. We'll talk a little bit about data in a second while we.
It's 1 arc second.
The seeing is 1 arc second, which means not good. Well, I mean, okay, not good for us.
Yeah, for this kind of telescope at this location, 1 arc second is.
And
not
for
the
what we're
best.
trying to do.
But for another location, like for instance at Texas UT campus in West Texas, where it is the McDonald Observatory, I think 1 arc second is amazing for McDonald Observatory. So it depends on where you are and the kind of science you're trying to do. 0.9.
Yeah, I blame me. Oh, John, You weren't here when we measured it, so it's gone up. So that might be because of you. Not that astronomers are superstitious or anything like that. Oh. I appreciate the knock on wood. Yeah. Oh, cool. Sam, yeah, if you wanna, so we didn't, did we mention that Keck is actually twin telescopes? So there's actually two of them. So why have one when you can make two for twice the price? So there's two different telescopes and they both have the same basic mirrors set up and all of that kind of stuff, but the instruments that are attached to them are different. And so Sam, one of our other AoTATX people, has used the other Keck, the twin telescope, to do, I assume, Sam, you've used it, to do some of his science. And that one has lasers. And so we don't get to use the lasers.
Actually, Keck 1 has lasers again.
Why don't we get to play with the lasers?
Because we don't do that science.
Fine. So bye, John. Thank you. Everyone go find him on the Twitters because he's awesome. And yeah, so the other one has lasers to better measure kind of like the atmosphere that you're looking through. And apparently they have a red alert, Star Trek red alert.
That's cool.
When there's some kind of restriction.
But also terrifying.
Because you can't always use a laser. You're not just allowed to shoot lasers into the sky without asking permission because planes don't like lasers being fired at them, it turns out. And
maybe, you know, if you took a green laser pointer and you shined it at a plane, you could be put in jail.
Don't do that, kids.
You would. No, you would. Not you could. Because it lights up their whole cabin. Like they can't see.
Yeah.
No,
don't do things like that. Yeah. So
can we talk for a second about the job they used to have? They might still do. I bet it's different now, but the job for undergrads at University of Arizona, you'd go observing at the MMT and on Mount Hopkins, and they'd have their laser up, and there was a job to like plane spot to make sure that you weren't going to fire the laser while there were planes in the sky. And so you'd have like a bunch of undergrads in sleeping bags lying in the parking lot, just like watching the skies. Because that's the kind of technology that we like to roll with.
High tech.
Oh man. I mean,
Sorry to interrupt.
No, that was totally worth it. Cash, I agree. I don't get to shoot lasers though, so I guess I feel like I have to have another point to what I'm doing. Space Command. Oh man, it's like my former life, man. Okay. Yeah, we're not allowed to play Galaga. That's cool. Well, happy early birthday. Luckily, the full moon doesn't matter to us. Normally, the full moon is not a great thing for astronomers since it's so bright. It's really hard to see like anything else that's up in the sky. And so, fun fact, we look at different wavelengths of light to look at different parts of galaxies or different things in the sky or things that are different distances from us. And so we are actually looking at things in infrared wavelengths of light. And so the moon doesn't actually matter too much. So you, with your own eyes, can't really see in the infrared. But if you're like night vision goggles, it's kind of the same. That's what you're looking at, as heat signatures. And so, was I talking too long?
I changed the cow. Sorry, keep going. Rude. You left the cow.
I don't even know what you're saying now.
Oh, I'm so sorry. Michaela, what was she saying?
What was I talking about?
I wasn't listening.
Doing great. So good.
Anybody?
At least we're taking data.
Cash, no, you can't kick red.
Oh,
No.
why the moon doesn't matter.
Oh, the moon does. Yeah, thank you. The moon. That's right. Yeah, the moon doesn't matter. Well, okay. The moon is kind of an important thing in like a general sense.
It does matter in real life.
It does matter. But like it is not a problem for us. It like being up and being bright and being kind of in the way doesn't matter because it's not very bright in the infrared in the wavelengths that we're looking at. And so so it turns out that oftentimes what the science that we're doing Josh, are you closing things?
Yes, yes.
The science that we're doing, we get time on the telescope when it's a full moon. And so unfortunately for people like me who have never personally seen the Milky Way by eye, when we go to places that are dark, where we would be observing, it's a full moon because it's convenient for us to be observing at that time since it doesn't matter to us. And so I have never, ever gotten to see the Milky Way by eye because every time we've been observing, it's been a full moon for a reason.
We didn't know that one.
Yeah, I'm super glad that you got to watch it. Space is pretty cool. I'm also slightly obsessed. I can't speak for everyone in the room. Jasmine does not care, but she's asleep. Cash, I'm so distracted all of the time. There was another question and I don't remember what it was.
Okay, you start reading those messages.
Well, that's what the questions are.
It was like, what are you going to do with the data once you collect
Oh,
it?
right. Do you want to talk about data reduction?
Okay, yes. So imagine if you've ever played with, like, back when in MySpace days, I'm aging myself here.
Oh, please.
I know. But remember, like, you used to be able to add like little sound clips or things like that, and you could like record your own music and upload it or your own sounds. And so imagine you're recording music and then you want to remove all of the static sound that's in the background. So you might then either use fancy software like we have nowadays, or you could just be completely silent and record some sound, and that would be your background static sound. And you can remove that from the recording that you made, and then you kind of have a really clear and crisp recording of your voice or whatever else you're doing. So in a very similar way, that's how we process this astronomical data that we get. And so it's a little more complicated. It's not just one step. There's a lot of different things you have to do. But essentially, we take these things called calibration frames, where you are essentially taking different kinds of calibration data to account for all the different things that might be adding light or noise to your data. And so for near infrared stuff, if you're getting to large enough wavelengths where things are glowing, you have to correct for the fact that the Earth is glowing at certain wavelengths. Because think near infrared, think of it like, or infrared, like heat vision. That's what that is essentially. Mm-hmm. You also have to correct for any kind of like little electronic noise that's being translated into light on your detector. You have to correct for a ton of other things too. And so there's, and before it gets dark, we usually do this around, if we were in Hawaii, we'd be doing this at 3 p.m. in Hawaii. So it's still light outside, and you take all these calibration frames, and then at night you're taking your science data, and you're able to, when you run this data reduction software, the software essentially takes the data you're taking and applies all of the calibration files you've already taken to subtract off all of the noise and come out with this beautiful, crisp and clean, awesome spectroscopy. And so that's kind of how the data reduction process works in very basic terms. Any instrument will have some kind of data reduction process. For the most part, if they're advanced enough, they'll have software available for you to just literally put in the files and press go, and then it gives you nice data products at the end. Sometimes you have to do your own, you have to make your own, which requires a lot of code, and it's pretty intensive, and you have to understand exactly how to account for all these things. There's also different processes, different kinds of corrections you do when it comes to spectroscopy versus photometry, or imaging, taking pictures versus spectroscopy. But for the most part, that's kind of how it works. And so then you get this beautiful data product at the end. And the Keck Observatory has really awesome data reduction pipelines. And the current data reduction pipeline used for Mossfire was recently upgraded to Python 3, which is the newest Python coding language version for Python, and was in large part upgraded by one of our former Texas A&M, now PhD, but Texas A&M grad students, Leah Alcorn, who's now a postdoc in Canada.
Oh yeah.
And she was a visiting scholar at Keck Observatory as well, working with Dr. Josh Wallander. So yeah, that's how we process our data. So.
Where does the clear processed file go?
We usually have it in the same location that we took all the other data. You can kind of organize your file structures differently, but that's really just up to personal preference. Based on the software, you might have to have a certain organization. But for the most part, yeah, we just put it where we want. If there's a particular spectrum you want to keep, you can go put it somewhere else, like wherever your working directory is, like where you're doing all your code and stuff. Yeah, that's essentially where it goes.
What do you do with it?
look for any kind of detection of any kind of light from our galaxies.
Hashtag science.
Hashtag science. We joke that we're looking for 4 photons, which is like, to translate, that's not anything. That's not enough. But that's mostly just kind of laughing at the fact that the stuff that we're doing, kind of like John mentioned earlier, we're pushing the limits of even like the best spectrograph, in my opinion, many people's opinions, the best spectrograph for near infrared on the planet. Like, we're pushing the limits of it. Like, we're right at the edge of what it can do. We really need instruments like the James Webb Space Telescope to get up in the air, in space, actually, not air.
I can't drink. I'm working.
Get into the vacuum of space and start taking data for us, because we need more precision for what we're trying to do. But because what we have right now is the best of the best and can barely detect them, we get like very faint detections, if any. And so that's kind of what we look at through this clean data. We're trying to find any kind of faint light from these galaxies. And it's really hard, because these skylines will trick you sometimes, and because we correct for them in part of our calibration process, but they definitely still exist in the data. And it's hard sometimes to tell if it's just random noise that you see, or if it's actually a detection.
Absolutely. I'm not knocking on dogs like yes. I didn't steal this dog, Cash. I borrowed her. This is my sister's dog, Jasmine. Say hi. Or don't say hi. I'm babysitting, and so she got to come to work, and she was excited for the first 30 minutes until she realized she's now stuck here. Yes, Taylor is absolutely the Sagan of spectroscopy.
I mean,
can we make that your new
I'm
name?
gonna add that to my CV.
Put that on your website. Yeah, no, honestly, you should check out Taylor's website. She's a boss ass bitch. And it's in the link, right? I put it in the YouTube video description link. What's that called?
The YouTube description.
Yeah, okay, that's what it's called. Look, you guys, I don't spend a ton of time being live on the internet. I don't know what you're talking about. So if you go check her out, she's super cool, and she's done a lot of stuff. So some of the things, the code that she's written is actually like she's made public so other people can use it. She's given a lot of really cool talks, and I think they're all there. I at least on the I link them. I link them everywhere. Yeah. Check her out. She's done some really awesome outreach things. She's done a lot of really cool science, and you can find out what makes her one of my favorite people. And
I believe you into making websites at some point.
Look, I have one.
You do.
It sucks. But yeah, there was, okay, hang on. There was another question. Some people think that SETI is a bit silly looking for aliens, but with the loss of Arecibo, is there any other site that's as important for SETI? SETI at home is pretty cool. I cannot claim to know a lot about SETI, and I don't think it's silly. I think that if there is anything that is the most exciting part of our field for just general humanity as a whole, is the prospect of finding other life out there in the universe. And so I think as far as like what makes astronomy to me interesting, and kind of like the gateway science to many of the other sciences, is that anybody can kind of be part of it. You can go outside and look up, and all of a sudden, like, you're part of what we do for a living, and you can experience looking up into space and seeing some of the things. And so potentially you heard about like Jupiter and Saturn being close together, and you could have just gone outside and looked at that. And so things like that are what makes what we do really accessible, and I think really exciting and interesting. Arecibo was devastating to see that collapse. That's a very important observatory, and I believe there are some. Didn't you say yesterday?
Yeah, I think there's the Puerto Rican government, I think, put out an executive order to put funding in. Mm-hmm. And then there's also several petitions and GoFundMes that are trying to raise money as well, because it is such a vital part of astronomy, but also their community. Like, it's super impactful and important.
Yeah, and so there's other ways that we can search for extraterrestrial life. I guess I should have explained what SETI stood for. And so we have several talks that we have on our Astronomy on Tap channel. So the YouTube channel, I need to learn all the words. The YouTube channel that you are watching right now has plenty of other talks from the past, what year is it? 6 years of Astronomy on Tap in Austin. And we've had several talks about SETI and kind of the history of it. I don't know if Sam is still here in the chat, but I know he's given a talk about the history of SETI, and maybe we can find a link to that talk he gave that gives some more information about all of the different kind of initiatives that have gone into searching for extraterrestrial life. But Arecibo is a radio telescope, and it's not the only radio telescope, but it was one that was predominantly used for those kinds of searches. But we also have lots of telescopes that look for exoplanets or planets that orbit other stars other than the sun. And so, current telescopes that do that kind of thing are always trying to look for Earth-like planets around other stars. Those are very hard to detect right now since other stars are quite far away. But we have found number of planets around other stars.
The thousands?
It's a lot.
At this point?
It's a lot. And a lot of them are more like Jupiter sized or more extreme because the bigger planets are easier for us to see, right? And so we're constantly trying to build better telescopes, not just for galaxies, which are cool too, like what we do, but also for looking for smaller planets closer to stars that would live in a thing called the habitable zone. Bad Astronomer is a good resource too. Oh, cool. I'm really glad you got a telescope. That's awesome. We have a couple talks and probably people in the chat that are amateur astronomers or people who have their own telescopes and like go out and do star parties and stuff like that. I don't know where you live, but there's typically, the dog is falling asleep and not exactly lightweight. And so you can probably look for like local star parties or, groups of people that go, that's really gross. People in your area that can go out and do star parties or bring out telescopes and look at different things. You can learn a lot from them. I learn a lot from them since I don't own my own telescope. I just hijack very expensive ones for work.
Very legally.
Just like I legally took this dog. And so I don't remember what the other question was. What does the spectra tell you about the galaxy you're looking at?
Ooh, that's a great question. So for the galaxies I'm looking for, these really early ones whose light we're seeing has traveled 13 billion years to get to us.
Just a bit.
First of all, because we keep mentioning how faint and far away they are and how we're pushing the limits of Mossfire to even see these galaxies, the first thing you can imagine is just getting that light. That's first thing. Like if we see the light, that tells us we know exactly where this galaxy is. When you get spectroscopy of a source, you're getting the exact wavelengths of light that these galaxies are emitting. And so this displacement, you want to show the redshift animation?
Where is that?
I'll send it to you.
Okay, yeah.
So the light, we'll show you an animation, but the light has been displaced so much that the first light we're seeing from these galaxies are in the near infrared, but that light was originally emitted from the galaxy in the ultraviolet. And so if you get detections of any kind of light from this galaxy in your spectroscopy, you're suddenly able to say very quickly and immediately and conclusively how far away this galaxy is. And so that is, first of all, is incredibly important because there are so few galaxies that have spectroscopic detections at these distances. And then the next thing you can figure out when you get these detections is, comparing to astrophysical galaxy models, spectroscopy, galaxy model spectroscopy, you can start to unpick what kind of galaxy properties might have created that amount of light, like the strength of the emission line, which is this particular wavelength of light that you might see. Like, is it a lot of stars, or is there a supermassive black hole in the galaxy that's powering a lot of light? You can kind of figure out begin to get like the telltale information about what's going on for galaxies in this time, because we know very little about them. And so the kind of getting spectroscopy of these things is really, I can't emphasize enough how important it is. So that's the kind of science you can start to do when you get detections. So.
Yeah. Oh, okay. All right. Jesus. Okay. We're good. Hi, Travis. Yeah, cool. Thanks, Alan. Yeah, Alan's definitely part of the Austin group, Boston Astronomical Society. Look, you guys, words are hard. Oh, am I sharing this? Okay. You know it's not easy? Finding your mouse on 3 different monitors. Oh, nice.
So this is an animation I made that she's about to show you that shows what you're going to see is a model galaxy spectrum, and we're redshifting it. And so redshift is the term that describes this displacement that you see when you're looking at galaxies farther and farther away. So as the Z number increases, the
oh, why did it do that?
Oh, weird. Maybe don't look at it that way.
How do I open it then?
I don't know. How are you doing? I don't know. You could also just like show the Slack.
I guess
open it in a new browser.
I could just do it.
I don't know how you do that. Okay, there you go.
I think this will work.
But yeah, so you essentially see that like what started out as Z equals 0, which means like if it was right next to us, what starts out in the ultraviolet by redshift or Z of 5 or greater is suddenly in the near infrared. So.
Are we good? Hey.
Oh, it's a lot faster on the Zoom. I mean, that's fine.
I don't know.
So if you want to describe any more of that, feel free.
Do it again. I'll point.
1 second, I need to check some things. So do you want to explain?
Yeah, okay. So like what Taylor was saying is this black line right here is the light emitted by a galaxy over a range of wavelengths. So here along the bottom, the x-axis here is the wavelength. And then here in the y-axis is like brightness, basically. And so when you take a spectrum of a galaxy, given certain properties that we've just picked, it will look like this. And then what you're seeing is as we take that same galaxy and we push it further and further away from us. So things that existed further back in time are further away from us. And the light actually gets stretched out over time as it travels to us. And so not only does it get fainter because it's far away, so you see the whole thing kind of dropping down lower in the y direction. But you also see the whole thing moving to the right as the wavelengths get stretched out as it travels to us. And so what you would have seen in the UV here in the purple, this big bright thing right here, actually gets stretched out into the infrared. And so the telescope is looking about right here as far as like what we're doing right now. And so we're looking for we're looking for these little things because this is your time. I look for this thing and then Taylor looks for these things, right? Yeah. These ones right here. Yeah. Oh, they move really fast. Okay. These are the the lines that we're looking for in Taylor's galaxies tonight. And so this is like carbon emission from galaxies that happens when stars get formed. And that can tell us a lot about like what the galaxy is made out of, how fast it makes stars. And then we can start to understand in context galaxies early on in the universe, whereas right now we can barely even just find them. And so what she's trying to do is learn more about the galaxy itself and not just find it. And so a lot of the targets that we have are ones that we have already found through like hydrogen emission. We can see hydrogen is super bright since it's the most abundant thing in the universe. And then Taylor is now trying to look for carbon emission from them so we can actually say something intelligent about the galaxy other than its location and distance. And so all I do is try to find things. What Taylor does is try to tell us something about them. And so it's actually pretty cool what we can do with just a few little pinpricks of light from a galaxy.
It's pretty impressive.
Yeah. And I hope that made sense. That went by a little bit fast.
That's a good question. So there's a question that says you're basing your observational plan using the model as a guide. Mm-hmm. If I'm interpreting that question correctly, Yes, loosely, right? Like, so we're, a lot of things in astronomy kind of amaze me that we're even able to conclusively say anything, because we're just getting light from space, right? Like, we are technically experimentalists in that we have a laboratory, which is space. The unfortunate side of being a physicist that does this kind of experiment is you don't get to control the experiment. You just get what you get. And so we have this light coming from space, and we have to
Space don't
understand
care what
it
you
is.
want either.
Yeah, it's just continually amazing to me the kind of information astronomers throughout the years have been able to pull out from just light coming from space. But so for the kind of galaxies that we're looking at, these really, really distant ones, it's in the early universe. There aren't many elements that have been formed besides hydrogen and helium. And so that actually has a lot of implications for the kind of light you would see from these galaxies. And so kind of building off of that and building off the kind of environments in the early universe we expect, you can have a really pretty accurate expectation of what the light would look like. And so using our models to kind of come up with this background expectation, we can say, okay, this emission line from carbon is probably going to be pretty bright. And so for these galaxies, we could maybe see them. And so in that way, yes, we are basing our observational plan on using these models. But once you get these detections, that's when the exciting part happens, because you have a detection, first of all, which is noteworthy on its own. People publish papers on individual galaxy detections, me being one of them, her being one of them.
People.
But then you can compare to these very same models and see, okay, well, we expected them to be about this bright or this strong, these particular emission lines, but we see it as this strength. What does this tell us? And so they're building together. Excluded because it's not stretched.
Yeah, Steve, that's definitely true. So when we are looking at a model, we get these models from like what we know of quantum mechanics. And so like hydrogen exists in a certain energy state and will always be emitting radiation basically at a specific wavelength. And so when you look for a bunch of radiation, you're hoping that it's hydrogen, and then you can like look for patterns. And so like it will have different energy signatures based on quantum mechanics. It'll be slightly different. And when you see that pattern, you know that that's going to be hydrogen. And then when you see that hydrogen signature, where you measure it compared to where it would be if it was like here on Earth, tells you how far away that thing is. And that's that redshift. And so if you see, oftentimes we have like things in the way. So what we're looking at is very, very far away. And yes, the light has had to travel like through space and occasionally other objects. And during that journey, it sometimes runs into other things. And so you can see like offset different signatures of things that it ran into along the way. And so I don't have a great visual of like that off the top of my head. I don't know, maybe Michaela can think of something. But when we're looking for our galaxies, we know what the signature is supposed to kind of look like. So her carbon emission actually is like two different emissions. And so if we see both of those things, we know it's carbon, and then we know it's her galaxy and not something in between. That's something different. And so there is some uncertainty in some of the things that we're looking for, especially if you're me and the thing you're looking for is hydrogen and it's the only thing you can see, you have to be very certain that it's not oxygen from a closer galaxy that kind of looks similar. And so not only did I spend a lot of time trying to even find the thing I'm looking for, I spent twice as long trying to prove to myself and to everyone else that it was what I thought it was and not something in between me and the galaxy that I was intending to see. And so you do a lot of that with using images of this galaxy. What's getting better? Is it because John left?
It's a little better, yeah. It's less variable.
Yeah, and so so there's a lot that goes into trying to confirm that what you're seeing is what you think it is. And we use data from other telescopes and images of a galaxy in different wavelengths. We can use all of the data we can have for a specific object from multiple different places to make our case that it is what we think it is. And so before even getting this time on this telescope, we have a bunch of images from the Hubble Space Telescope of all of these galaxies. And images are just basically average that spectrum over a longer wavelength range. And so you get less precise spectra.
Michaela sent me a paper.
Oh, we're looking at papers now.
Helpful visual.
Oh, nice. I guess I could open that since I'm the one that needs to share things.
Also, then I think you should, like, next topic after, I think Taylor and Rebecca, you should show your paper, like what the spectra look like once they're fully reduced and what your carbon-3 detection would look like. Like
That's a good idea.
from your other paper.
Yeah. Good at figure 3.
Cool.
Maybe not the publisher one. Oh, no, you're on UT Wi-Fi. It works. How nice. I get the VPN into
Oh, yeah. We're already physically here. Figure. Oh, look at it.
That's a very helpful figure.
Thanks, Michaela. That's pretty.
Yeah.
So we're going to look at one of Michaela's papers. Where the frick did my window? Jesus Christ. Hey! Unnecessary. Jasmine, calm down. There's no one out there. Come on. Jasmine, it is 12:45 a.m. There should not be anybody in this building. Okay. Where are we? Aha. Michaela, do you want to talk about this since this is your paper?
Okay, I'm gonna go back.
Okay.
I mean, sure. Yeah, this was just as like an example of sort of what you were talking about, where you might, like in the top row, is showing an example of an emission line that's created from hydrogen. That's the Lyman alpha line in the top row, and that's what Rebecca wants to find. That's what would be emitted. It's emitted by all galaxies, but you would observe it closer to the infrared, the near infrared, if it were redshifted, if it were really far away. So that's what we want to find. It's a signpost that we've identified galaxies that are really far away in the early universe. But we don't know that what we've seen or what we've detected is Lyman alpha for sure. So one of the ways we can tell is by looking for other lines or signatures or bits of light, little blobs of light that we see in the spectrum.
Blobs of light. I like it.
For example, if what we saw instead was a different hydrogen line, the hydrogen alpha line, H alpha, at like a redshift of 0.4, which means it's much, much, much closer to us, we might also see other lines at redder wavelengths. And that would be, in this case, it's sulfur 3. And then, so there's all these examples, like you could be looking at oxygen 3, and then you'd expect to see H alpha, you know, at a redder wavelength. So this is just a sort of a cartoon example of one of the ways that we try to narrow down what we're actually observing. If you see one blob of light, you know, it could be Lyman alpha, or if it's a different line, then we know, as Rebecca described, we know from quantum mechanics where we would expect to see the other additional strong emission lines. So we know that a galaxy that's forming a ton of stars, if we're looking at oxygen 3, we should also be able to see some strong H alpha. And so we know exactly where to look for it based on the quantum mechanics of where we would expect that line to be, and also where we would how far away that galaxy would be if what we're seeing is, you know, oxygen 3. So this is, yeah, that probably didn't.
And they also
sense,
look different too, right?
Right,
This is hydrogen, right? Hydrogen looks like this if it's this particular version of hydrogen, and it would look different if it was a different version of hydrogen coming from like a different physical process happening in the galaxy, and it would have this kind of feature to it. And so not only are we looking for like just this little peak right here, we're looking for the shape of it, anything that's nearby it. Like Michaela was saying, do we see this feature here? And then we also see these other ones off to the right. And then whereas oxygen, which would be this one, looks different. And these are all, like we said, based on quantum mechanical properties of what's going on. And how all of that works, which is a subject for another day. And so oxygen in a different location, and because of a different reason, oxygen would look this way, but it would also have this right here is this over here.
And so you can see that's a good point. Now we're getting into the weeds here, but you can see Rebecca just pointed out the two different oxygen 3s. Can you highlight those again, the orange one and the red one?
Sorry, there's like a weird lag because I'm like not on. Yeah.
But you can see, so that's exactly the same line as Rebecca said, but they look different. And so what this is also showing is that as you go to further redshifts and the lines are moving to redder wavelengths, the shape of the profile is changing as well. So there's a lot built into what we observe. It's not just the physics of the galaxy, it's also has to do with both the distance to the galaxy and like the features of the telescope that we're observing it with. Yep.
Yeah. So like, yeah. So we have the two oxygen, but then this hydrogen is the same as this hydrogen is the same as, oh my God, this one way over here. And when I'm moving to the right, I'm getting at longer wavelengths. So it's stretched out further. And so this would be the closest object. Then if it was further away, this same feature would be shifted to a redder wavelength or a longer wavelength because it got stretched out as the universe expanded. And then again, this galaxy would be even further away because the same feature is showing up at a longer and longer wavelength each time. And so none of what Taylor is looking at is in this particular diagram.
Yeah, my bad.
Oops.
No, it's fine.
But this is the same kind of concept. So how would I know that the thing I'm looking at is hydrogen at this distance versus this distance versus this distance? And that's because of all of these other things that you would be able to see and how that changes its shape and location basically in your data. I hope that made sense.
Yeah, I'm sure it
It probably didn't.
Sorry, everybody.
Feel free to ask follow-up questions. Because yeah, this is like Taylor said, everything that we know about these galaxies is basically just by looking at light. And so I can say something about physically what's going on in the galaxy if I see this versus this versus this or versus this. And so it's kind of insane to think that all we ever do is look at light from a galaxy and then we can use that information to talk about physically what's happening in that galaxy. Oh my gosh, Michaela, you know what I have the iPad propped up on? I have the Galaxy Formation Evolution textbook.
Nice.
There's freaking pictures in that. Like,
that's a really good textbook.
Yeah. We're not going to show people textbooks.
No.
Do you want to show around the goose?
That's for 3 a.m., not just 1 a.m.
That's for later for people who are stopped. Okay. What do you want to show?
So we're at a good time where we could show you all the rest of the GUIs or the windows that help us control the instrument.
Sure. What do we want to start with? You want to see what we're doing?
Yeah.
Which one do you want to start with?
Let's start with, well, we've seen the data one. We've shown them what that one looks like.
Yeah. We can go through all of them again. There's different people.
Yeah.
Right? Yeah.
Sure. Let's start with this one.
That one? Okay. Do I have that one open? I do. No. Yes.
So you're going to get to see what we're looking at.
Here's the control panel. Oh, I hope this is okay. Ta-da, internet.
What do you mean by okay?
Just show.
Oh, I think so. So what you're seeing here is essentially how we set up all of the things that we're looking at, the kind of spectroscopy we're doing, and then how long we're exposing for. And as you can see, the green bar at the very top is where you're taking data right now. So if you want to move away to the next one.
We're switching screens?
Yeah, look at the data one.
Okay. This is not a very quick process.
Yeah, you're gonna jump back and forth. She has a lot of windows open.
There's so many windows. Keep checking that it's okay. Yeah.
So this is one you've seen before. This is showing just a random, what we call raw frame. This is not corrected. It's about to update. There you go.
Hey.
This has not been corrected for any kind of background noise or any, cosmic rays or anything, or the skylines or anything like that. This is uncorrected, very raw data.
This is just the image we just took right now.
It just updated in front of our eyes.
Whoa. Do you want to do the tabby thing?
Yeah. And as you saw before, if we press tab,
Your head's in the way.
it does a difference between the two frames, and you'll see the two dither positions that we have. In this,
What are these right here? What's this?
Those are the stars.
Why do we have stars? Are we looking at galaxies?
Yes. So we always, as a rule, we in our observations, we always put 2 stars, slits on 2 stars. And this is partly because it's useful when we're calibrating the data to the proper, like, actual brightness from the galaxies, you know, after correcting for all of the noise and stuff like that. But also because it helps us track this, the precision of how the telescope is following and how Mossfire is following this galaxy over the course of the night as everything's moving across the sky. And so through looking at these stars and how their position vertically and their little slit changes is how we figured out that there is a very, very, very slight movement that's happening. And that's how, when we were talking about earlier, that's the very, very fine tuning precision that we need for the kind of hard science that we're doing.
Yeah.
Where would the light that you're looking for from your galaxy be? And now, no, acknowledging that you're not going to be able to see it.
Yeah. So this particular image, right, is 2 minutes, and we need 6 hours to see what we're looking for specifically. We can show you what it looks like at the end of the day when we add up all of our 2-minute exposures, so you can see what it looks like. And I can pull some of that up in a second. But unfortunately, the things like we talked about before are super faint that we're looking at. There's a really bright galaxy in one of these, and I don't remember where it is. Oh no, that was in the other band.
Oh yeah, we changed it out.
JK. There's something in the way in our data, and there was a really bright galaxy that we could just see very well last night when we were taking data, but we were looking at a different spot, and so I don't know where it is here, but we can show you what those things kind of look like on a good day when it's a bright galaxy.
If you want to, we probably shouldn't show the mask because coordinates over there. But
Yeah. I
can
don't know
maybe-
where my mouse is now.
Let me see if I can move them. Sorry, we have to be a little bit careful on the things that we show you because we have
Because the internet.
People can Google us.
I mean, you can Google us anyway, but like,
Yeah. But sometimes people in our field like to steal things. So let me see if I can pull it down.
wait, what was I supposed to show you, Travis? Wait, what do you, I couldn't see the chat earlier, and I think we're behind by a bit. I don't know.
I think
Are
it
we
was,
showing that or
I think
no?
it was when we were saying this. I think this is safe.
You moved this part? Yeah. Okay. We can probably show this. Okay. Let me find it on my computer.
It just shows the center coordinates of the field, which anyone can get.
Which window is that? Yes, this one. Yes, this one.
Yeah. So what you're seeing here is, this is called magma, which is
the coolest thing.
I think it's an acronym, but it might not be. Anyway, it's how we actually arrange the mask that will have the little slits and how we decide what galaxies we're looking at. You might hear the fan of her laptop.
My laptop's having a time, you guys.
But essentially, these are all the different galaxies we're looking at. I could show you all of them, but I won't. Because you have to be a little careful here. But yeah, so essentially, this is what we do when we're looking at what we call a standard star, which is just a really bright star in the sky that we use and that we know exactly, for the most part, what its light should look like at each wavelength. And we can use that to calibrate as like an additional step, calibrate all the data we get. And that's how we get the exact brightness of these sources. That's how we, after we do all the other calibration correction, that's the final step, which is what we call flux calibration. So this is how that mask is set up. Notice that most of these little bars, which are tiny little slitlets, they're not used. Just these center ones are. And we look at this big star. And we did that before we started this live stream, so you don't get to watch that.
No.
But this is what we're currently looking at. These are all just tons of different galaxies. And I'm not going to highlight any specific ones to you.
This is what tells the telescope instrument what to do.
Yeah, and so essentially we're taking spectroscopy of all of these dots, which is really exciting. So yeah, that's what that one looks like.
Mm-hmm. Yep. Mm-hmm.
And then
Where's the last window?
and what is the last one? The last
This one?
Yeah, it would be that one.
Where's that one?
Okay.
I mean, it's right there, but like, where is it? Oh, we could show this. We'll do that in a second.
Oh, yeah. So fine.
This one? This one.
There you go. And so this is the final one. You saw this before when we were showing the video of the Myra, the little thing where we saw the footprint of Keck, like the 36 segments. So on the left-hand side is showing you, we're looking at a guider star with a little guider camera, which just helps us be very precise over long periods of time and looking at our particular source. And then the next little panel was something that we did right before we went live, and this is using some alignment stars. So these are stars that are in our science mask that
Can't go back to.
we're not going to go back to it. But essentially that just helps us make sure that we're exactly centered on everything properly. So you can see these little white little bells, and that's what that was. And this is one of the steps too, is just this fine alignment process.
These are all stars.
Yeah.
That we're using.
We
So like we said, the Earth is moving, right? Like it spins, you know? And so as the Earth is moving, we want to make sure that we're still staring at the same exact spot in space. And so we need to guide on something, and it needs to be something bright enough for the telescope to be able to follow it. And so that's what you're looking at, is like, this is the thing that the telescope is following, so that we know that we're pointing at the same spot as the Earth starts to rotate throughout the night. So it looks like the stars are moving, but it's actually us that's moving.
Yeah.
Mm-hmm.
The Earth is moving. So yeah, so that's the 4 different VNC windows essentially that we use to control the instrument, and it's super great. And you have to monitor all at the same time, while also simultaneously monitoring the weather and monitoring everything else.
There's so many things open. We could show this one.
Yeah,
this one. It's over there.
Oh yeah, we're showing. You wanna? Yeah, doing great.
It's over there on that screen, except you're seeing it and we can see it. Anyway, it's great. We're doing great. Anyway, this is a thing.
Ephemeris.
Yeah, that's a word. This is a thing that is showing us like how high in the sky what we're looking at is going to be throughout the night. So like this is sunset, and then this is sunrise over here. And then so you'll see like how high up in the sky the thing we're looking at is right here at any given time. And so I don't know what time it is.
We are UTC 658.
I can't see that.
Oh,
here.
You're about right there.
About right here. So this is where we are as far as like up in the sky from Hawaii, right? Not in Texas. And then this is our standard star that we use. And so we just have it here to track. And then this right here is the moon. So the full moon is up and super bright right now. And we talked a little bit earlier about why that's not a big deal for us, because it's not bright in the wavelength that we're looking at. And so this is how we kind of know when we can start, like how this grayed out area right here means it's too low for us to be able to see with the telescope. And so once there's a lot of things that are popping up on your screen. Sorry. There's a lot of numbers. So this once it gets above this kind of like grayed out area here at the bottom is when we can start to look at it. And it has to be also dark enough. So it needs to be out of these dark blue boxes for us to start taking actual science data. And so that is another thing that we have open to kind of track where we are, since we're not physically like looking, we're not anywhere near the telescope. Where did my Zoom window go?
Which program is this?
I observe. It's only on Mac.
It's a Mac thing.
But you have my other laptop, Michaela. It's on there.
Yeah, but my favorite. Okay, yeah. I was just like, I've never seen this before. It's so much.
Yeah, there's no Linux equivalent, unfortunately. Which Michaela and I are both Linux people. Because
I just have a Mac laptop.
Rebecca
I'm a Linux person.
She's also a Linux person.
I just wanted iObserve. Yeah, it's some person made it. I forget his name, and I want to give him credit, but I don't know. But it's iObserve. And like it knows where like the observatories are and stuff. So you just are like, hey, we're gonna observe at Keck, and here's the coordinates of the thing I want to look at. And so yeah. The witch. Yeah.
Yes.
Oh, yeah, cool. Did you take pictures of the NeoEyes? Was that it? Was that just July? Was that?
What is
It's
time?
December. It's almost January.
It's almost
Oh my
2021.
Jesus Christ. Yeah, it's the same, right? Because the Earth is spinning, right? And so things in the sky move, or appear to from our point of view. And so, yeah, in order to take pictures or to track on things throughout the night, you have to move your telescope to follow that same movement. And so these are all things that kind of go into how we have to make sure that we're collecting data.
Mhm.
And it has to be super, super precise all the time. Yeah, hey, that's cool. I always wanted to like do that, the
Do it.
astrophotography, but I don't have the patience to do things like that. And I don't have any of the equipment, and I feel like starting from scratch would be really, really difficult.
Oh, Josh shared the link for iObserve.
Oh, thanks. Thanks, Josh. Do you want to like introduce the other people who are here? Like Taylor and I and Jasmine are in Texas right now, remotely controlling all of these things. But there are people in Hawaii who are, where did you send me the link?
Slack.
Okay, cool. This is how you find iObserve. Oh yeah, ArcSec.io. Thank you. I couldn't remember what it was called. Here is a link for a similar program that will help you like show you where things are. I put it in the chat. Yes, there's people. There we go. That was what I was talking about. There's people in Hawaii at the telescope on like the top of the volcano. And there's people also working in Hawaii who are helping us control the things from here. And so we can see if they are available to say hi right now, since we're in the middle of a very long sequence of exposures.
There will be the occasional cow still.
The cows are not going to go away.
Every 2
If
minutes.
the cows go away, you guys, please start screaming at us, because then we've not been paying attention and something isn't working.
Yeah, if you hear a witch and then no cow, 2
Ooh,
minutes later,
that'd be bad.
that means I missed my button and I need to press.
I missed my button. Did you ask them?
Yeah, so I offered Josh if you wanted to join the other one, so we can still hang here.
Sure.
All right. Oh.
How do we do this?
Maybe we'll just have him go to the other one. Let's have you.
Well, the people, they can't join the other one.
Oh, that's true.
The People Summit.
Okay, well then hand to him.
This is gonna get janky. Okay. We're gonna point this camera
At laptop.
at a laptop in another thing. So you want?
Yeah.
You're okay. Cool.
Hey Josh.
Hi, Josh. We're going
to
do this.
rotate the camera. Is it okay with y'all?
Yeah. You gotta turn it.
I don't. Sorry, you're looking at my face. Okay, I'm gonna rotate the camera. Here is. Oh no! How is this?
Stop
going?
moving. Stop moving.
This will be fine. Nope, we're not.
Your fingers in the camera.
Oh.
Can you flip the camera so you can see what you're doing?
Yeah, y'all, we're gonna. This is high tech, and there's a case. We're taking off. Nope, the case is not. There we go. Okay, y'all. Here we go. Hey, Josh, and there's Carolyn too. Hello.
Hey, everyone.
So Josh is our support. Josh is our support astronomer, and then Carolyn is the current. It's observing assistant, right? I keep saying operating assistant.
Yes, sure. Yeah.
Yeah. So,
She is where we would normally be.
yeah. So Carolyn is in the actual observing room at the Keck Observatory. That's normally where we would be, and then Josh is working from home, doing also the remote observing. And then this top panel you're seeing is on the summit, but people aren't. Oh, hello!
Oh, hello!
Yay! Someone at summit. Hello.
Thank you.
Thank you for making sure everything works properly. Yeah, would you like to say anything? Or, whatever. World is your oyster. Oyster?
Oyster?
I'm doing great.
I think you guys are doing great.
Thanks, Jeff.
The thing looks like it's behaving. That's good. Well, I just said that and then looked at the guider full with max, and that's gone back up. Never mind.
Don't talk about it.
I'm not going to talk about the
You
scene
can't
anymore.
mention it or it's going to get worse.
Yeah, that's pretty bad.
I closed it. Don't look at it.
Thanks for closing it.
Don't look at that.
Anyway, full steam ahead.
Yeah. Does anybody want to does anybody have anything fun to show? Look at how many monitors that she has. We're short a few. I'm jelly.
I know, it's amazing.
Yes.
Please
show us.
please show us.
Yes. Your monitors are way more than ours.
I know. There's like 8 up there, right? Or can you not move it?
Not without unplugging it.
Oh no.
I have 13 monitors in this room, and I think Keck 2 has more.
Wow, really?
Oh,
I didn't know
all?
that.
Oh no, I have, including the one I'm talking on, I guess I have 15 in this room.
Wow.
Do you want to talk a little bit about what they do?
Yeah.
You don't have to. You can tell us.
You don't have to introduce yourself if you don't want to.
Nope, I'm good. They tell me if the weather's good, what the telescope is doing, and the main person's Carolyn, not me.
Yeah. If anything breaks though, you have to fix it. So.
Yeah. But I have someone on the phone telling me how to do that the whole time.
Very important.
Yep.
Thank you.
Thanks. That is cool. I didn't realize there were that many
That's so many
things up there. All right, I'm gonna stop looking at y'all's faces now. So you're free. Goodness, I'm so sorry.
Oh my god. This is no, it's gotta flip. Sorry. We're gonna make this the most awkward we can. Okay.
There you go. You are now getting the insight that very few others who don't observe get to see. All the cool stuff and the amazing staff behind it and all the amazing things they are able to enable for us. And
And the cow.
the cow.
Yeah. I don't know where any of my windows are anymore. That's not what I wanted. So does anybody have any questions for us about what we're doing, what we're not doing?
What does the carbon-3 look like when it's
Well,
all done?
Very good question. Thank you for reminding
Taylor,
us.
you got to do things while I try to find all of our data. Because
You can just pull up my paper.
which paper?
You
You can just, where is that?
Here, I will send you the link. I search it often because I have to go look up coordinates and stuff. And
Thanks,
so,
guys. Thanks for watching. I'm glad that we were able to do this.
yeah, I'm impressed.
Have a great night.
I'm impressed with the people who are sticking out with us, and staying up so late.
We've got 3 more hours, so
Yeah.
you don't have to stay up.
So
with
while
us.
Rebecca looks at that link, when you observe on these telescopes, you obviously, anytime it's dark in the night, through the whole night you get to observe. In the winter on the northern hemisphere, the nights are longer, and so you observe for longer, and so you could be staying up for a very long time, which is why we sleep during the day when we're observing.
Is it this one?
Yeah, and then what's cool is this is a recent thing, I think, in the past 3 or 2 years, that Keck has been doing what we call half nights, where if I just care about one particular field, that wouldn't be up the whole night, and we'd only see it in a portion of the night, then I'd only want really that part of the night. And so they've started doing a thing where they'll give a certain number of observers the first half of the night to look at stuff, and then we switch over and give the second half of the night to other observers. And it's really cool. And so we actually only have a first half night tonight. And so we only have 3 more hours with this telescope. But if we were doing the full night, we would have 9 more hours with this telescope.
Oh,
So
yeah.
we probably won't be staying up for with y'all for the whole next 3 hours. Just spare you.
Whenever.
But
Whenever.
but yeah, so
No
that's how
plan.
long our half night would be. Is about 6 hours.
Are
you sharing?
Thanks, Jeff. It's a dress in his pockets. Also, hi. How are you? Well, the paper.
Yes. Oh yeah. So one sec. Starting a data download. There you go.
I can't do that. You
That's
won't
okay.
let me
Don't
do
do
that.
So
Taylor has banned me from opening more things on my computer and then continues to send me links to open things on my computer.
yeah, I do feel that.
So
way.
for the record,
Her computer's gonna,
it's already, it's fine.
its life expectancy is very short because she keeps running way too many things at once.
Okay. There's only 1, 2, 3, 4, 5, 6, 7.
It's at least 25.
There's only 30 things open.
All right, so what you're seeing here, if you want to zoom in full screen, like do the bottom right, the little like, press it twice to make it do the,
This?
yeah.
That made it smaller.
No, one more time. There.
Whoa.
So what you're seeing
I
here
could do that.
is a plot from one of my papers. So this top left image, if you want to put the mouse over there,
This
is an actual picture of this galaxy. This is using Hubble Space Telescope data, and the colored boxes you see overlaid are different Mossfire slits. That's just kind of showing the different ways that we've oriented the telescope and Mossfire to look at this data through the different years, from 2014 to 2017. And so we were taking H-band spectroscopy, which is a pretty red or large wavelength region, larger wavelengths. And so what you're seeing on the right-hand side here is the actual detection, the original detection of the hydrogen line that Rebecca looks for at even higher redshifts or further away from us. So this line, like she was pointing out, is the first thing you'll see in these galaxies, usually. And you have to try really hard to prove that it is an actual detection of that and not some lower, like closer galaxy that has a similar feature that is fake. But so this detection was actually, Mossfire was commissioned on Keck 1 in 2012. And in 2013, this detection was published. And at the time, it was the highest redshift, the most distant galaxy ever discovered. And that detection was done from data using Keck Mossfire by her boss, Steve Finkelstein, Professor Steve Finkelstein.
That's whose office
we're in. So it's kind of like this nice full circle.
Hi, Steve, if you're watching.
So what you're seeing here is actually a combination of that data and then many other years of data all put together, all using Keck Mossfire. And this was a spectrum pulled from work by one of Steve's former students, now PhD at NASA Goddard, Dr. Inte Zhang. And so this is just showing that beautiful detection of Lyman alpha.
This is hydrogen.
And so if you scroll down, that's the data that I took. And so this is the carbon emission line. And there is a detection there, which is just so exciting. And so from both of these detections of these different like emission lines of these different wavelengths for this galaxy, you can not only get the distance to the galaxy, which is slightly different for the two, you can also start, like we talked about earlier, start comparing to your galaxy models to try and understand, okay, well, based on what we understand astrophysically about how this light is created, what galaxy properties match this observational data that we're seeing. And for this galaxy, we found that it was, likely get stars, 300 times the mass of our sun, like lots of powerful radiation pouring out of this galaxy, and then not very many elements heavier than hydrogen and helium. There's what we would call metal poor, which essentially is just a fancy astronomer way of saying that there is not many elements heavier than hydrogen and helium. We've essentially called anything that's not...
Wait, did you just say metals?
Elements, sorry. Not any element that is not hydrogen or helium, astronomers would call the metal.
Just don't think back to your chemistry class and whatever you learned about the periodic table, anything that's not from the Big Bang is metal.
Yep, essentially. But yeah, so that's all of that insight we got for that galaxy was literally just from this little detection using the most, or I'm gonna have to say one of the most, but in my opinion, it's the most powerful near-infrared spectrograph in the world.
Mossfire?
Yeah.
Hell yeah, it is. That's why we're using it.
Everyone's jealous when they hear that we have Mossfire time because Mossfire is amazing. But yeah, so this is like a legitimate, you're looking at real astronomy data here.
Oh, that was another question we had earlier.
Real astronomy data?
No. What's the proposal process like? How do you get time on this telescope?
Oh.
Like, why do we have time? Like, how?
Yeah, if you want to, we can stop sharing if you want.
Oh. Sorry, you can keep talking about it.
No, that's it. That's all
I just remembered.
If you have any questions about that data, feel free to ask us. So when you are applying for time on a telescope, generally the way you do it is like you can't just say like, hey, I want time. And you're like, okay, great, here's the time. Like, whenever you want, just
Sure.
roll up and use this telescope. Usually you have to apply for time, essentially. And so especially with these bigger telescopes that are incredibly important and that everyone wants to use, are very powerful and massive, all these things. You have to try really hard to convince them to give you the time. And so you're applying with, and competing essentially against hundreds of other people who are also applying for time. And it's even harder when you're applying through like a particular avenue. So the Keck Observatory is co-owned by University of Hawaii and many University of California
UC school
schools,
system and Caltech.
and maybe something else too. I might be misremembering that. So you
Caltech.
just, yeah, and Caltech. But you can also look them up just to get the full list of
There's a link to the
co-owners.
observatory website in the
description.
thank you
The
YouTube
YouTube
description.
So if you're part of any of those university systems, you have a smaller pool of people that you're competing against. And so you have a higher chance of getting time on the telescope. Not that it's any less challenging. It's just the odds are better. The odds are more.
Well, they own the telescope, so they have more.
yeah,
nights.
you have guaranteed time if you own part of the telescope.
They built it.
So the rest of us, you have to apply through time that is owned by NASA. And so NASA owns a certain number of nights every semester or every half of the year. And they're able to give those nights away to people who apply. But the hard part about that is anyone who's not part of those places I just mentioned has to apply through this avenue. And so the oversubscription is what we call like 4 to 1, like or 5 to 1. Like it's really hard to get time.
For every night, 4 people want it.
Yes, every single, yeah. It's really hard to get time. And so you have to write these proposals where you're essentially describing the science in a way that any astronomer, even one who's not in your subfield, can understand and appreciate. And then you have to motivate why Keck and the particular instrument you want is the best thing for answering this question for you, for your science, and is the only thing that can really do it. You essentially have to like sell it. Like, I need Keck, I can't use any other instrument or telescope. I need it, please give it to me. And then you have to lay out a plan of like, okay, I want 1, 2, 3 nights. I'll do this kind of data. Like I'll take a lot of images or I'll do spectroscopy, and you kind of lay out, and then you kind of lay out with this data, I can answer these science questions. And so like there's this whole process, and then you submit that, and there's this group that meets called the Telescope Allocation Committee, or the TAC, and they meet and they decide, they rank all the proposals and how good they are, like the merit of the science and how well they've proposed and things like that, the feasibility of the science, and then they assign days or they assign nights to each of the highest ranking proposals, and they essentially just have to schedule and fit everything in. And that's essentially the whole process of proposing for time. It's really challenging, but the fact that we ever get time is amazing, and the fact that grad students get time is even more unheard of. Like when we get the emails that say like, hey, you've gotten time, they always say doctor, like by default, because it's not common for grad students really.
I told my boss, okay, I can graduate now. I
Um,
already have my doctorate.
but I also want to highlight that Rebecca in particular has gotten a ton of nights awarded
I'm
through
not talking
through
about me.
NASA.
This is your night.
This is my night, but this is my second time getting Keck time awarded. So I've had 4 nights awarded, but Rebecca's had like 8 nights over 2 years awarded for some amazing science. And so, and you get money with this too, because you're applying for grant funded time. And so NASA will also give you money. I think it's like about $17,000 to do your science and pay for your papers and
Depends
travel
on
and things
all
like
the
that.
things, yeah.
So it's really amazing and important for our science, but also just for career development to be able to do this. So
Yeah.
general summary, how
Yeah.
it works.
Jeff just asked if multiple people can get overlapping time, like if we're looking at similar data, but with different like science in mind. And it's funny that you ask, because that's why we work together. So we are doing technically different science, but we can use the same telescope and the same instrument and look at the same wavelength. And since this particular telescope and instrument are able to look at more than one thing at a time, we can look at like something like 30 different galaxies all at once. We proposed time, and we made the argument that primarily at the beginning when we were doing this before, I was leading the proposal and my science was the primary science. And then we said, but it's not just going to enable us to do this kind of thing that I'm trying to do. We also are going to use the same time, the same instrument, and look at the same wavelengths and be able to do even Taylor science as well as some of our other collaborators. And so we made the argument that with all of these 30 objects that we can look at once, they were all going to be scientifically relevant in many different ways. And so part of what we proposed for was giving multiple researchers time at the same time. And I think that seemed to work well since we got time. And so now the nights that we're observed, like right now, what we're doing is Taylor's science is the driving science for what we're doing. And then mine, I don't even have anything.
Yeah, not this time.
It turns out
We're not looking at a field that you like.
that I don't like where we're looking. And so so typically we argue for our time, saying that we can do more than just one thing with it. And I think being able to be creative with and collaborative in our science is what I appreciate the most, because not only does it mean that we get to observe together, but I think that that also makes for a more efficient use of a telescope, and also really exciting things that I get to be involved in that are not necessarily something that I would know anything about. So we have collaborators that are like, oh, you're pointing at that part of the sky. Like, I have something super interesting right there. Maybe you could look at that too. And then I get to learn about what they're doing, because now I have data for them and kind of understand that kind of stuff. And so, yeah, I really like that astronomy is super collaborative. And like we showed you, it's not something that like one person can just go and put a camera on a telescope and take data and do science. It takes an entire team of people. And I think for me, that's one of the more exciting parts, is that we have people who are in Hawaii, we have people who are in Texas, we have people helping us from different locations, and all working together to make the most out of one night of data. And I think for me, that's a pretty cool opportunity to get to work with a bunch of people.
Yeah, it's one of the best ways to start collaborating.
Yeah.
With people.
Yeah.
Put the money proposals.
Yeah. And so, other people will get time on a different telescope, and then we might not be able to propose for that, but they can, because it's a telescope that their institution owns. And so we, collaborate together and pool our resources. And so things like that make what we do possible. And so I think, it's interesting to note that, that like working together is one of the coolest parts of astronomy to me, since, I can't go to space and look at a thing. I need a telescope that is run by a lot of people to go to space and do that. And I need, a team of people at the summit to drive the telescope so that I can operate a camera. And I need other people to give me things to look at so that I can make the most out of it. But I'm gonna get off my soapbox.
That's a good soapbox.
Can I add?
Yeah.
I also like that you don't need to spotlight me. That's fine.
Yep, we're doing it.
I also like that, even if, now I lost my train of thought because I'm staring at my own face. Another aspect of that is that, once the data are taken, even if you weren't a member of the proposing team or a collaborator of the proposing team, almost all data from almost all telescopes ends up being public eventually, like after a year or so, giving the team time to work on it and see what they can find. It still is, the images, the spectra all get public in a big database that you can sort of query. And so years and years and years later, people will still be using the same data set to look for new thing, like, people will be thinking of, what's this like brand new way I can sift through the data and try to find interesting things in it, and they can look back over years of observations, because astronomy is space doesn't change that fast, and so that's kind of nice. Or anyway,
do you want to describe the Hubble archive?
No.
It's just like a really great.
Michaela's face is like, no,
It's a really great example of that, right? Like
Mass.
people still go through that data.
That needs to go outside
and publish stuff.
I will be right back because the dog needs to go outside.
Spotlight her so she's not staring.
Yeah, Taylor. Yeah, what Taylor was talking about is exactly what it's a perfect example. MAST is the perfect example. It's an archive that holds all of Hubble data, and you can go onto this sort of web form and put in a set of coordinates, or put in like the name of the person who proposed for time. You can search by almost anything, and it will pull up all of the observations that Hubble has ever taken with any instrument of that position of the sky. And that allows you to sort of sift through and say, okay, well, these exposure times were too short for my science goal, so I don't need those.
Yeah.
This is the wrong wavelength range, this is the wrong instrument, but here's a whole subset that I want, and you can download it all, and you can reprocess it if you want to clean it a little bit better than it was, or you can use the data fully reduced and sort of see what you can see. So that's that's cool. Since Rebecca just left, does that mean I'm spotlighted the whole time?
No, I can switch back to me.
Thanks,
to spare you. you don't have to be stared at the whole time. Yeah, no, it is really cool. I also like, I'm gonna briefly continue on what you're saying. I also really appreciate that data is available publicly after some number of time. Like it is stressful as the observer to be like, oh no, I only get like a year and a half to work through this data, because everything takes a long time, especially if you're in grad school. But it is really cool though, because I mean, for instance, Mossfire is an incredibly precise and amazing spectrograph, and the stuff that it looks at is fantastic, and the data quality is amazing. And so like having that data available to other scientists after a certain period of time is just invaluable. And so I do really appreciate that. And Keck also has their own archive of all data from all of their instruments, and they have like 8+ instruments on the 2 different telescopes. And all that data after the proprietary period is passed, which is about 18 months, becomes available, and you can use it. And like Michaela was saying, you know, look at if it's enough exposure time for you, and if you're looking at an object you're interested in, you can use that data, and people definitely do. So it's really cool.
Yeah, and this is all fun and games until we start dealing with things like the LSST, the Rubin Observatory, where we're getting like terabytes of data, and we can't save everything, and that's a whole new problem for astronomy. But for right now, it's a really awesome feature.
Yeah, it is really funny. We're kind of, I wish I could, can we side by side? No, probably not. I feel bad that now you're talking, we can't see you. But astronomy is really funny.
Cool.
Like, we're always pushing the limits of instrumentation and technology, really, right? Like, so like, for instance, the science that Ruck and I are doing, we're using Mossfire, but like Mossfire can only barely accomplish what we're trying to accomplish for our science. And like, it's the best one out there. And so that's why we're talking about the James Webb Space Telescope, and how when that goes up, it will revolutionize my subfield of science, because we'll be able to get better data than we'd ever had before, because it's gonna be really awesome data in space with a 6.5 meter wide telescope. But like Michaela pointed out with LSST, which is, or the Vera-Rubin Observatory, which is gonna be this massive, I think it's 30 meters or pretty close, which will be in Chile, and we'll just be taking data every night of the sky and generating terabytes of data every night. Like, I don't know if I think they're still trying to figure it out, but like literally just storage for data is not like how like how do you store that much data that is being generated every single night? Petabytes.
I mean, right. And the answer is that you don't. The answer is that you have to throw out a lot of it. And so the question becomes like, how do you decide what's interesting?
Yeah.
Nope.
We're going back to you. Yes.
Yeah.
Oh,
I was done talking, so
I was hoping you keep talking. Wait, I don't know how to switch back. But yeah, no, they're generating so much data every night, and so not only do you need to figure out how to qualify the data, but also how to store it, because you need to have this for many years in the future, and so you probably have to build facilities that are simply existing to store data, which is kind of crazy. But oh, cool. So Josh added a note in the chat that said all the data from all instruments back to the founding of the observatories is on the Keck Observatory archive, which is super cool. And so you could just plug in coordinates and pick any instrument you want, and then it'll tell you what, and like a search radius. Like, so you put like a circle in the sky, and it will return anything that has data in that circle. And so any galaxy or star or anything will have data, and it'll tell you what day that data was taken and all that stuff. So it's really cool. Oh, cool. So there's a question about, do you guys have a team of software developers you can contact to create tools that you may want or need? Fantastic question. For the most part, the observatories, if they're able to, and if they have the funding and the person power, they will create the software reduction process, the things that will clean our data and make it pretty for us to use for the final products. And you can collaborate with them or talk to them about how to improve it. Like, they definitely, every observatory needs feedback from observers, like for everything. Not only making data reduction processes more efficient or more effective or things like that, but also running the telescopes better, just making everything more efficient, how to improve the instrument, things like that. And so observer feedback is always like a really valued thing. So we can always talk to those software developers, but in some cases, if you're part of a collaboration, like of a large number of people who are taking and you got awarded a lot of time on a telescope, and you're going to be taking data on a ton of different things and build up like a massive catalog of sources that you have data for, and you publish it. That's what we call surveys. And for collaborations that have surveys and have these big amounts of data, they often like to create their own software reduction. And so they'll use some kind of coding language. Usually it's Python, but some of the older ones use IDL. But just some kind of coding language, and they'll create it that will process the data. And it probably, if the data reduction software exists from the observatory, it'll usually be pretty similar to it, but everyone likes to do their own thing sometimes. And so in that case, you have software developers in your own team that are also probably astronomers and also doing science.
So I do think that's an important distinction to make, right? Is that there are like legitimate software developers, and then there are astronomers. And astronomers are, by and large, definitely don't mean to generalize, but I'm including myself in this, horrible computer programmers. We do it all the time, and we get the job done, but it is not pretty, not, efficient, not the right way to do it. But we write our own code all the time, and so there may be. So right, just to make the distinction between I'm definitely not going to call myself a software developer, though I've written many pieces of software that function, but I'm not sure anybody else would ever want to use them.
That's a really good distinction. It definitely, I think most astronomers I know, I could say it's probably a fair thing to say 95% at least of astronomers are self-taught when it comes to code. Like they might have taken some coding language like in high school or something, or undergrad, or something like that. But for the most part, all self-taught, and I definitely am. So that means that while you developed the knowledge to do whatever you need to do for your science, there might be some very key basic
structural
practices.
Yeah.
It's like your basic foundation isn't 100% stable because you didn't take you weren't classically trained as a computer scientist, and so there's going to be pieces missing from your knowledge simply because you weren't trained. You just learned as you went. And so that's most astronomers.
Yeah.
So I think, if anyone looked at my code, I do have my GitHub. I do share it with people, but I tell computer scientists I meet to never look at my code because they probably cry. Because they probably would hate it.
What?
Hey, puppy. Talking about coding.
Oh. My favorite?
Oh, speaking of people who use IDL, who should be doing Python.
No, excuse me. It works.
Gets the job done.
It's all I know.
I don't know how long you want to do this live stream for. But,
I know. Do we have a team of... Oh, did we answer all these?
Yeah, we answered it.
Space is huge, so yeah. Oh, yeah, cool.
Great contribution.
I need more coffee. You want your Red Bull?
Not yet. I'm still finishing my coffee.
Yeah, I didn't have a time scheduled to end.
We could loosely plan to end around. I think we're gonna. Yeah, we could loosely plan to end around 2, unless we get an influx of a ton of questions.
Sure.
Or y'all can watch us work.
I'm not allowed to work.
You're just not allowed to run 12 things at once on your poor computer. So
12 more things at once. There's more than 12 things right now.
She'll run her laptop to the point where it's worryingly hot.
It'll get over it.
And I normally bring this cooling pad
loud.
I have that gamers use to run tons of things at once, but I forgot, and so she's not allowed to do lots of things right now because her laptop's.
I could show you what it looks like to reduce data, but
her laptop's already very loudly. It's going. Yeah, I don't think it's gonna. You're slowly reducing its life expectancy.
oh, there's a request for Jasmine. Come here.
Jasmine.
Oh,
Here we go. Jasmine, how do you feel about tonight?
she is over it so much.
How often does she visit?
No, that's my face. What?
How often does Jasmine get to in the before times?
In the before times, I typically, Jasmine is my sister's, and I typically have her on Wednesdays. And so Jasmine, Okay, camera
Yep,
hog.
you know what you do.
She is typically here on Wednesdays, and so she comes to work and is very familiar with the building, and that was my eye, and is very confused and upset right now why there are no other humans here. She typically wanders the halls and says hi to everyone. Get out of my face.
We all have treats in our desk for her for when she comes to visit.
She went to Kelly's office twice now
Sure.
and like waited outside the door. And I was like, there are no cookies in there because there's no person in there. And she did not understand. It was quite sad. So poor dog. And it is also very far past her bedtime. So she doesn't know why we're here or awake.
That's fair.
Yep.
That's a great question.
Mm-hmm.
Observing is not as exciting for our little puppy assistant.
No, she doesn't seem to be all that interested in it. I would have thought that she would care about the cow noise, but she does not care about the cow sound. I didn't even notice it. Oh, gross. Whoa, close that.
Tonight has not been the best for
The weather?
the weather. So, that's not good. Maybe we jinxed ourselves by doing the live stream.
Well, I don't know.
So I created a code that, for any of you who aren't familiar, there's a drift. But also just might be how the seeing's bad.
Okay.
I created a code that takes our raw data frames and looks at where the star is, which we showed you earlier. You can see it in the raw frames. And it essentially tracks the vertical location of the star in its slit for each frame, essentially. So you can think,
we're following.
yeah, so we want to make sure that, that it doesn't move. If it doesn't move at all, it's precise. And we kind of mentioned this earlier, like that's how we can make sure that most of everything is precise as we would like it to be for our really difficult science. It's fantastic for everyone's science, but like for people who stare at the same place for more than 6 hours, we need it to be really, 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 really precise. So my code I wrote can check this. And so essentially it can tell us not only, what's going on with the atmosphere and how easy it is to look through it, which is something we call seeing. Imagine so brief aside, for seeing, it's a fancy word we use, but essentially imagine you're looking at a wood table and there's a knot in the wood and you put a glass of water on top. And so if your glass is still and you're not pushing the table or anything, you can see the knot pretty clearly through the water, like if you look down at the bottom of the glass. But if you were to move the glass or tap the table, the water starts to move and suddenly what you're seeing, the knot of the table starts to distort. And so the image of the knot is being distorted by the water. And so in a very similar way, that's how the atmosphere unfortunately works for us. And so when you're looking up at a star, for instance, if the seeing is really bad, it means there's the atmosphere is not playing nice. And so what we're seeing of literally the image of the star, if we're going to take images really quickly in very short images, the star might move around or look like it's moving around. It's actually not. It's literally just the atmosphere refracting the light and making it look different. Same thing is really important in spectroscopy. And unfortunately, we have fairly bad seeing tonight. This is unfortunate, but you really can't control the weather. We do joke that
why not though?
In a perfect world, there'd be no atmosphere, but then no one would be alive.
I mean, I like breathing, I guess.
Breathing is nice.
But it's kind of a pain.
This is why space telescopes are cool, because there's no atmosphere in space. You're in a vacuum. And so no seeing. The seeing is perfect. But yeah, and so we also the code tracks the seeing and also tracks how the star is doing vertically, like if the star moves at all for each frame. I just ran that. That's what our reactions were to.
We saw the plot of it not being good, and we both went, "Oh, close it. Don't want to look at it." Because there's nothing to be done about it. There's nothing to be done about it. So it is nice to know for when we want to reduce our data so that we can do science with it. But right now, luck of the draw, I suppose.
It happens. It does kind of inspire astronomers to develop superstitions about ways to convince the weather gods to be more favorable.
True. We sacrificed a car once.
People have rituals. There was once this really fun Twitter thread that we started by accident because we were talking about, it was one of the times we were physically in Hawaii observing, and one of our things, we would always go get poke, and then we would get these really bizarre candies that don't taste very good to us, at least. And then we'd eat those anytime the seeing became bad that night. And it was not an enjoyable experience, but we thought that maybe that would make the weather gods happy through our pain and would increase make the seeing better. Who knows if it actually works? But other people had these rituals that were like the day they were observing, they'd go eat a particular type of noodle, or they'd go eat some pho. Like,
Yep.
It was a whole thing. And so
It's just like people who have like who have routines on like before like sports games, I guess.
yeah. Oh, that's a good point. Yeah.
Yeah.
Anything where you think like following a routine would make you feel better, or at least even if it doesn't change the weather, it makes us feel more confident about the observing.
Right. Then I feel like I didn't do something wrong. Okay. All right. Okay.
Jasmine's gone.
We're over it.
Yeah. So if you ever meet another astronomer, you should ask them if they have any routines or superstitions.
I
about
guarantee
observing.
you they do.
They'll tell you all about it.
Yep.
You have to bring blue corn chips with you.
Is that part of yours?
I don't
Yeah.
think we have those.
Yep, you have to have blue
We have
corn
regular
chips.
corn chips.
No,
and
blue corn.
portions.
No, it has to be blue corn chips. You can have those
Well, you didn't
also.
tell us before.
That's probably why our seeing's bad.
This is all your fault. No, it's John's fault.
Oh, John knows.
That's true. Did it get any better?
It didn't get better.
Okay, we won't talk about it. Yeah, Jeff, if we just put all the telescopes in space, that would make it like way cooler, way easier,
It's true. It would be great.
way more expensive.
There was actually, we can make sure to not talk too much about this because it probably would make some people angry. But Starlink
Ugh.
is the big constellation of satellites that Elon Musk and SpaceX kind of put up without consulting the whole astronomy community.
Without caring.
Without
Not
caring,
without
yeah.
consulting, without caring.
So one of the things it's doing, aside from destroying a lot of data all the time, is that we're taking from the ground. Is it's just interfering with so much stuff. Like when you're observing from the ground, you have a ton of things happening, like we talked about. But you also sometimes have satellites that go overhead. So if you're taking big images, like what we call photometry, with some of the big telescopes down in Chile, for instance, you get a really beautiful picture of a big field of the sky, and you get a lot of galaxies and stars in that. You probably, every 6 images you take, you're probably going to have this bright streak go across, which is a satellite that's gone across, and that's just expected. But when Starlink first went up, when it crosses, that whole image is ruined. Normally you can correct for the region that the satellite goes across, but all the data is ruined. And so it's really
the worst.
It's really unfortunate.
There's a picture.
I don't know if it was ever going to be avoidable if that kind of system was put up in space, but it was unfortunate that more communication did not happen.
Travis, I'm sorry, but I disagree.
But yeah, so it's just unfortunate. And so the frustrating thing about that is one of the things that this person said whenever astronomers as a community came out and said, hey, this is awful, please stop, or please find a way to fix it, please make them paint them black, make it less reflective, just do something, please. And their response immediately was, oh, just put telescopes in space. It's like, do you understand?
Oh, okay, you put the telescopes in space.
It is the Keck telescope, I think, is currently $10 billion.
Is that it?
But I mean,
JWST.
no, sorry, yeah, I meant James Webb, sorry, not Keck. The James Webb Space Telescope is currently $10 billion. And so it's expensive. I mean, as you might expect, to get something heavy and big and incredibly precise up in space. Like, you have to fund all the people who build this stuff. This is one of the example of an image that's been ruined by the Starlink constellation.
These streaks right here. So what what we're doing is we're taking 2-minute exposures. So we open the camera shutter for 2 minutes. And so right here, this is the camera shutter that was open for some number, I don't know how long. But during that time, the satellites moved through the field of view. So basically moved in front of the camera. And so what you're seeing is space not moving, but all of the satellites going through the images right here. And so in order to do any science, if I was looking at this particular galaxy right here, there's no way I could see any of my stuff anymore, because I now have to remove this entire streak from my data, and I've lost a significant portion of my images to this.
Yeah.
Bullshit.
Normally you have only 1 or 2 of those lines in that amount of in that kind of image.
Yeah.
So it's just it's unfortunate.
That example is a very early constellation of
Oh,
stars.
right.
If it's even Starlink, like they're even worse once you get the full constellations going. The other thing is that there are some wavelengths of light that you need to observe from the ground. Like, you know, it's $10 billion to put James Webb up, but who's putting a radio? You can't like send a radio dish into space. I mean, so you know, and Starlink is just as, if not more, you know, disruptive to radio observing. So like,
Yeah. Another
It's
example.
just getting worse.
Yeah.
Yep.
So it's frustrating. But yeah, so the comment of, you know, just put everything in space, and so you don't understand how hard it is. Like, yes, ideally, all telescopes would be in space, but that's not how life works. Everything's really expensive, and it's hard to get stuff up there. And so also the telescopes that are currently up there, everyone needs them, and so everyone tries to get time, and so they're incredibly oversubscribed. And so, no, it's not an easy fix.
Did you see the one, it photobombed Hubble?
Did it? Oh yeah.
Did you see that?
Yeah, it was like one of the first times that Hubble was ever photobombed.
So we
by a satellite.
put.
oh no, Hubble gets hit by satellites all the time.
Oh, does it really? Okay.
All the time. It's
This
just
is
that
also-
they're not as bright because they're
For people who are unfamiliar, Hubble is orbiting the Earth, whereas, for instance, the James Webb Space Telescope will be not orbiting the Earth. It'll be out at a different point in space. So, that's why Hubble could be
Where's
photobombed,
that
but James Webb
picture?
can't. But
I
if
know
James
I
Webb is, that's interesting for other reasons.
What the heck? That is going further away from where's that picture? I know I saw it on Twitter.
Hubble being photobombed?
Yeah. I'm not gonna find that anytime soon.
Anyway, that's my little brief aside that might get some people mad, but it's a very unfortunate thing that's been happening recently in astronomy. So, we're not in astronomy, but to astronomy. So.
Elon's like, it'll cause zero problems for astronomy. And astronomers were like,
Did you ask us?
Exhibit A, Exhibit B, Exhibit stop doing this to my data. And then they painted them black and then they were brighter. I don't. Whatever. Anyway, enough about that.
In this whole time that we've been talking, we have taken about 50, almost 60 images, or spectroscopic images of the galaxies we're looking at. So y'all have been a part of this process for taking 60 spectroscopic images. Very exciting. So if you were watching this the entire time, it's updated 60 times. Fun fact. The more you know.
What?
If they were watching this,
I get it.
Data, they would see it like refresh 60 times.
Anyone been counting? I haven't even been counting. That means you've heard 50 cows.
That's a really good way
There
to put
you
it.
go.
Well,
You can count the
I was
cows.
changing the sound occasionally.
Oh.
You've heard at least 50 cows, maybe not 60. That's a great point, Jeff.
Just saying.
But yeah, so if y'all were, one day when we're all allowed to like actively travel and do things again, if you ever find that you're near a telescope, like an observatory somewhere, or you'd like to travel and go see one, most observatories will have visitor centers where you can go and see, really beautiful pictures of some of the data that's been taken. You could buy swag for the observatory, support them, potentially meet people who work there. It's super cool.
Also get a tour. Some of them have tours.
Some of them give tours.
Yeah.
They can take you up to the mountaintops and give tours.
Yeah.
The McDonald Observatory in West Texas is gorgeous and beautiful, and the telescopes are gorgeous.
We're not biased.
I love it. I got to hug one of the telescopes. It made me super happy. But,
All
right, you ready?
What are we ready for?
We're gonna restart the 10 repeats.
Oh, we're gonna have a witch sound.
And then a cow.
And then a cow.
A witchy cow.
Witch cow. I don't know if anybody has any questions about something other than what we're doing. But in the meantime, I was going to show this. So we are not currently in Hawaii. We are not currently at the telescope. But in today's age, that's fine. We can still see it. So here's several different webcams that are on the summit of the volcano in Hawaii, and are like live views of what's going on. And so we, where's the one? It's nighttime, so a lot of them are dark. Is this the one? Oh, look at that. So there are several different observatories on the summit, and some of them like point at other ones. So you can see some of the different telescopes, and I don't know if Josh is here, but I can't tell them all by which. So that is the end of our script. So we do a bunch of repeats, and then once it's done repeating, we have to restart our little macro. Yeah, there's a bunch of different views of the summit. I think I put this link in the YouTube description. And so you can kind of see the view pointing north. There's another telescope in the view there, and pointing south, you can see there's a couple of different domes. So these are all different telescopes. I don't know if they're all operating tonight or not. We can kind of see, this cannot be right now.
I think it's old. Well, I mean, they actually,
What time is it
they
there?
changed the exposure and saturation.
That's true. I mean, it is though.
It might look like daytime, but it's actually nighttime.
It's because it's a full moon. It's so freaking bright.
Also that.
Is this Orion right here? I can kind of make it out. So this is the view from the summit. You can see some of the telescopes are up here, and then this is looking up at the sky. It's super bright because the moon is bright, and these cameras operate at wavelengths that the moon is bright in. And so you can kind of, if you're interested, the link is in the YouTube description that has any of these cameras that you might want to check out. I'm also going to show you, this is the Keck Observatory website. This link is also in the YouTube description if you're interested. It talks a lot about the observatory that we're using right now. So these are the twin telescopes we talked about a little earlier, that we are using one of them, but there are actually two of them. We are using this one right here. You know, there's some really cool discoveries that have been made using this telescope that are not just, you know, ours. But you can learn a lot about some of the science that they do and some of the things that we have going on. The Nobel Prize in Physics was recently awarded to an astronomer who has data, like some of the data was from this observatory. And so there's a lot of really cool things that have come out of this telescope facility, or both of these telescopes here. And so, yeah, the link is here. If anybody's interested, you can, you know, do some stuff. I don't know where your recent talk is, but Taylor gave a talk.
Oh, I think it should probably be in events. Yeah, so that one.
Look at you. That's you.
That's me.
That's you. Yeah, so Taylor recently gave a public talk. That's you and the telescope. That's not from today.
That's not from today.
Yeah, so she recently gave a talk about some of the things that we're doing and the science that we're looking at. And so if you're interested, this is the information for that, and it's on the Keck Observatory website, because Taylor is awesome sauce. And it's a really cool talk, and she did a great job. So you should check it out. And I guess I can put that link in the thing. Watch. You can watch. Everyone can watch me copy paste some stuff. There you go. Yeah.
You essentially would just hear a very fancy, more like well thought out version of what we've been talking about.
A shorter version of tonight's
the kind of science that we're doing.
Yeah. Yeah. What else did we want to? I thought there was something else we were supposed to do. But I keep thinking
we're just
that,
hanging out.
and I don't know what that is. Yeah. So we're here. If anyone wants to know anything, or has questions or whatever.
If we do want to end it too, that's in 5 minutes.
Yeah. So I suppose unless there's any like last minute anything, we're probably going to end the live stream soon. Thank you for watching with us, and I hope that it was remotely interesting as we remotely control the telescope. Anyway, all right. I'll leave the jokes to Jackie. So we are going to be here for a few more hours before we hand off to the people who have the second half of the night. But check out Taylor's talk, learn more about it if you're interested. We have links to her website where she's talking a little bit about what we're doing and why we're doing it. And she has a lot of her really cool science results. Those are all in the YouTube thing.
Description.
Description.
I don't know, that's such a hard word for you.
Look, I don't know. I feel like I need to like play Jackie's little like subscribe, blah, 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 button, push here, whatever's. But I'm not the YouTube star that she is. So yeah, if you have any questions, you can reach either one of us. Our websites and things are in the description as well. And thanks, Jeff. I really hope that it gets clearer too.
Hope the weather clears up.
And yeah, potentially we will do more videos like this randomly in the future. And Taylor also is part of Astronomy on Tap Bryan College Station. And so the link for their YouTube channel and some of their videos and talks is also in the description if you're interested in checking them out. And yeah.
That was a great summary.
I might not have been listening, but also also we've got, did you mention our little form so people can ask questions?
Oh, I didn't.
Cool. Go.
Well,
you're highlighted.
One moment while I go find
Mike has to find
we can
it.
talk about
So in these new times when we are attempting to become YouTube stars, and
We're doing
so far
great.
we're doing great. It's gonna be. We have a Google form that you can ask anytime an astronomy question, a space question, anything remotely adjacent to those topics occurs to you. You can drop that question into our form. We'll get it, we'll collect them, and we'll start answering them in either short videos or longer videos or live streams. But we'll start collecting all of your questions the way we used to do on the trivia forms when we were in person. And this will, and so this will give us a chance to still address your burning space questions, while we become streaming stars.
Yeah, stars. Well, I guess it's an appropriate term given our subject matter, but I don't know if
we are stellar people.
All right, it's pun time, so I think we're gonna log off. We put the link to our website. So our website is AoTATX.org, and that button to ask us questions is like nice and big and burnt frickin' orange. No,
Okay.
I guess I could do that. And burnt frickin' orange right there in the middle of our website. So if you are interested in asking us any questions, you just click on this. And then all of our social media stuff is here. And I don't know, there's a whole website. It's pretty cool. Michaela did an amazing job. You should check it out. Yeah. So that's all. I think.
Thanks for sticking around.
We have.
She's still highlighted.
No.
Look at that one.
No, I think we're good.
I think it's fine. It's all good. Okay. Thanks for tuning in. Bye, everyone. Until next time. And maybe we'll do a video showing kind of the results of the data that we took at some point later to upload for people who might be interested in and seeing the science that came out of it.
We did a little flash talk.
Yeah, that'd be super cool. No promises on that happening quickly because it's not easy to do, but yes. Cool.
Yeah,
thanks everyone.
Thanks for sticking out so long. This is fun.
Yeah.
I'm glad y'all were able to join us for this. And anyone who's watching this post live times, thanks for watching.
Post live times. Yeah. All right.
Bosco's here.
Oh wait. No, we
What
gotta
a
see
lovely
Bosco.
ending.
Okay, we gotta get Jasmine and Bosco. For this bye. Come here.
Jasmine's like, no.
Not again. Ooh. Oh, heavy dog. Okay, no, that's my face. I know I deserve it. Where's Bosco?
Maybe not. Maybe we won't get Bosco.
Maybe we don't get Bosco.
Let's try to coax him in.
Bosco's a little too big to pick up.
He's
Jasmine had no choice in the matter.
Yeah. He's a very sweet old man.
No?
No, he's going back to bed.
Oh. Well, we were tempted with the thought of seeing Bosco, but
We were gonna let Jasmine
Sorry.
and Bosco say bye.
Aw. Sorry to hold you all up.
No, you're good. All right. Bye, everyone. Thank you for watching. We will be here all night.
if you miss us, go play cow sounds on YouTube. It'll be the same experience.
All right. Bye, everyone.
Bye. All.